to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support, and that support allowed us to have this summer school happen. And I'm extremely happy to see all here today, both on Zoom and parallel stream session on YouTube. I would like to note a couple of organizational and technical details, even though some of you might have been in our previous workshops and already know them. I'm still going to repeat for the new crowd. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself and do not turn your videos on unless you have a question. We'll really ask you to put questions in the chat. That way it's going to be easier to handle the questions for the instructors and for the support team. But if you want to speak up, of course, you can raise your hand, and then whenever there's going to be a time, we will let you unmute yourself and turn your video on if you want and ask a question. If you're in the parallel stream session in the YouTube, you can leave your questions in the comments in the live chat, and we will handle those questions either in the chat directly, or we will direct the questions to the instructor. And I want to remind all of you that today's Zoom session is being recorded, and I'm thanking you all in advance for following this etiquette rules. And we are continuing with our 10th workshop in the summer school series. We already passed the half of like the meat of the summer school. And today we also continue the yesterday's workshop, or it's a new workshop, but in a way it is a sort of a continuation. It is a natural language processing topic modeling, and we have again, and we're very happy to have again Professor Dirk Hovey as our instructor today. He is an associate professor of computer science in the Department of Marketing at Bocconi University and the director of the Data and Marketing Insight Research Unit at the Bocconi Center for Data Science and Analytics. He works in natural language processing, a subfield of artificial intelligence, and his research focuses on computational social science. He's interested in what language can tell us about society and what computers can tell us about language. And as usual, Dirk, the floor is yours, and you can share your screen now. And thanks, everyone.
Thank you very much, Olga. Thanks, everybody, for being here. Very happy to see so many people interested in the topic. And yes, I assume some of you have probably already been here yesterday, so good to see you again, see in quotation marks. And we're gonna, have the same structure as yesterday. I'll start out going through some of the background, some of the theoretical underpinnings of topic models, sort of embedding it in a larger context, a little bit of NLP. That's going to be the first half of the workshop. And then the second half, we will go through a Colab notebook together that I've prepared with some data and some code that you can run also on your own. That sort of gives you a working or two working topic models, a regular one and an author topic model. And if you're wondering what those are, then fret not, because we're going to clear all of that up. Okay, let me share my screen here. There we go. All right, so I hope that is working as intended. Okay. So yes, oh, by the way, if you have questions throughout at any point, please do ask the questions in the chat, or by raising your hand and interacting with the moderators who've done a fantastic job handling those questions yesterday. Always happy to take a question when it arises. That's probably the easiest way to go about it. I should say some of the things we're going to talk about are going to be a slight repetition of things we have talked about yesterday. So if you were there yesterday, that's going to be, a little bit of repetition for you, and you can feel smart in the knowledge that you already know these things. But since we have a couple of new folks, I want to go over those things. Otherwise, might not make as much sense. Okay.
Sorry to interrupt you, but there's a pops-up screen, build order.
And it's not going away. Okay, let me. Yeah, what is that doing there? Okay, let's see. Okay, let's see whether this is better now. Does this work?
Yes, looks good. Thank you.
Okay, so you just have the screen and it
Yes.
switches. Okay, great. Okay, so I assume most of you are here because they already have a sense of what topic models are. So for those, I want to talk a little bit more about the details today and what topic models can and crucially what they cannot provide. I know sometimes topic models, can seem a little bit magical because they are the strange thing. You just throw some text at it and then you get topics back. But I want to, sort of discuss a little bit the parameters that go into it and the conditions under which we get, the best possible outcomes, and a couple of things that we need to keep an eye on in order to make sure that what we're getting out of it is really what we want to get out of it and not sort of just some random output. We're going to cover latent Dirichlet allocation, which is sort of the granddaddy of topic models. There are different ways of topic modeling, I should say. You could also even do topic modeling using simply dimensionality reduction techniques like singular value decomposition, and then you can use that. Latent Dirichlet allocation is sort of like a text-specific way of clustering things, and it has proved to be very useful, but there are many iterations on top of it, and we're going to also talk about a variant of that, the structured or author topic model, which is very, very useful if you have meta information about your texts, some covariates, for example, you happen to know who has written the text or which country the text comes from or things like that. And I want to talk about, really the nitty-gritty, the bolts and what have yous that go into making a topic model work. So these are statistical models. So there's a couple of parameters and knobs and dials that we can twist and turn and twiddle with to change the output slightly, and we should know what they do in order we're not happy if we're not happy with the output in order to make it the way we want. Okay, so to put this into a slightly larger context, topic models are a very famous application of natural language processing, but there are more branches of this field, subfield of AI, which in itself is a subfield of computer science. So there's one branch that deals with generation. Those are things like chatbots and smart speakers, smart assistants. Those are things that have seen an incredible boost in recent years due to neural networks and renewed technology and just more data. But we're not going to cover that here. And then there's a whole branch that deals with understanding text. So taking text and basically telling us something about that text. There's one branch in this subfield where we look at patterns in the data. So that can be imputation of missing values or the prediction of outcomes based on text. This is what we've covered yesterday if you were here. So classification and prediction, those are things like, is a text positive, negative, or neutral? Can we predict whether it was written by some specific author we're looking for or not? Which region was this tweet sent from? Things like that. And today we're going to look at the other branch, which is exploration, which includes a variety of techniques. So something like word embeddings, word vectors, also something we briefly covered yesterday, but that also allows you to do some, get some insights and do some, sort of societal diagnostics. We talked a little bit about that. There are things like clusters, simple clustering techniques that allow you to sort of group together texts or group together pieces of the data you're working with. And then there's topic models, which is what we're going to look at in depth today. And like I said before, you could, if you wanted to, conceive of topic models as like a text-specific clustering technique. So it really is a way to get at latent groupings in the data, but those are based on textual features. And hopefully that will all become very clear throughout the day. Topic models have been used in a variety of things. So Telly et al. Used it to basically group and then visualize where all of the funding goes to. Many national research councils have, large pots of grant money that gets out every year. And so an interesting question is obviously, where does this go? And, can you sort of like get a sense of, how the money is being used? What are sort of the topics that get researched by most of the money that comes from certain agencies? And so topic models are one way of, getting a sense of those things. A former student of mine, Han Nguyen, was actually using topic models to get a sense of what is going on in the smart speaker market. So if you buy an Amazon or Google or Apple Sonos smart speaker, then you might, look for certain features in that. And she found that there's basically 8 different aspects that users look at and value to different extents when they buy these smart speakers. And she found that, there's actually a clear separation in the market between Amazon and Google smart speakers on the one side, and then Apple and Sonos speakers on the other side, where people are, people who are interested in sound quality seem to go for the Apple and Sonos smart speakers, or, maybe if they have those, they really notice the sound quality. So that seems to be a difference. So smart speakers can help us, get some insights into a large amount of data and sort of group it into more manageable chunks. We can sort of get a sense of what are the big streams, the big topics, the big themes that are going on in the data. Was there a question in the chat?
Yes, Didier asked, is topic modeling or supervised or unsupervised modeling?
Topic modeling, yeah, that's a good question. Topic modeling is generally an unsupervised technique, because you're not providing any labels a priori. There are ways of adding supervision to topic models, and we're going to look at that later, which oftentimes can make sense. In many cases, especially in social sciences, you already know something about the domain you're working in. You happen to know something about the topics you will most likely encounter. You might not know all of them, but you might know that you'll definitely see something about environmental issues, or reproductive rights, or some other topic that you as a domain expert know is in the data. And semi-supervised or not fully supervised, semi-supervised approaches exist, and we're going to see a little bit of that later. The authored topic modeling or structured topic model that we're going to look at is essentially, structuring the learning process in a way that involves some outside information. But the sort of quote unquote vanilla topic modeling is completely unsupervised. You just take a whole bunch of text, you stick it in, and then, out comes a bunch of topics in some way, shape, or form. And so one thing I should say is, to many of you that will probably be obvious, but maybe not to everybody, topic models don't give you the name of the topic. So here you can see price, integration, sound accuracy, skills, fun, ease of use, and music. Those are labels that Han gave to these topics after the fact. The topics are those word lists that you see on to the right there, right? So it is really also something that requires your interpretation of the word lists of the topics in order to come up with a label. This is not something the models do for you. They just give you these lists of words. So, and that is, can be tricky. So if, you got a word list, a topic back that consisted of the words pasta, pizza, wine, sauce, and spaghetti, do you intuitively think, yes, this is a topic? Could you come up with a label for that? Probably yes, right? This would be something like Italian food, or food in general. So, most people would probably look at that and go, yes, I think this is a topic, right? But what about this? Bleu, bird, encoder, decoder, transformer. So, cheese, Sesame Street, I don't know, like electronics and then blockbuster movie, right? Or not? Well, in this case, this might seem like a random collection of garbage words, more or less, but it turns out this actually is a sensible topic. Bleu is a score to measure the quality of machine translation tools. BERT is a model, it's the name of a model, bidirectional encoding of something transformers, which uses encoders and decoders and is an example of the transformer neural network architecture. So this second one actually is a sensible topic, but you would not know this unless you are a researcher in NLP and probably specialized in machine translation, neural machine translation. So how sensible a topic is something that requires our attention, that requires our interpretation, our, sort of like domain knowledge and a human eye on it. So the machine can pre-sort, pre-structure things for us, but then in the end, it still needs this human in the loop. So how does it work as a pipeline? Well, we start out with a bunch of text, like so. We pre-process this. That is, we remove any noise words, anything we don't want, and we're going to talk about this in more detail in a second. We will then set up our topic model of choice. There are several topic models you can choose, and all of them come with a number of parameters. The most important thing is to determine the number of topics you would want to get out of this. And then there are a couple of other parameters that you might or might not want to set, and you will iterate this step. So that's why there is this circular arrow to basically go through and find the best combination of topics and parameters that give you an output that you are happy with, that you're confident in, that this is, the most sensible way to get information out of the data. So despite what topic models sometimes are portrayed as, it's not like a fire and forget one-shot thing. It does take some care and some information. There's actually a fantastic paper, Care and Feeding of Topic Models, by Jordan Boyd Graber and et al., that sort of goes into details of all the things that affect the quality of your topics. And a lot of that happens before you even run the topic. We're going to talk about that. Then you get out your descriptors, things like this. Those are the topics, just lists of words. For example, the top 5 words in a topic. And then you can come up with a label of these topics. And then you have a model that you can use to either label or get the distribution over those different topic labels in each of the documents. But you can also use it, of course, on new unseen documents and sort of get the distribution over topics in those new documents. So you can, then see that this new document is to 50% about the food topic and 30% about travel and, 20% about leisure and fun or something like that, right? Yes, question.
Yes, there was a question sent through a private message, I think accidentally. With new language generator models like the GPT-3 available, would it be possible to replace the human in the loop element with a summarization layer to automate the whole pipeline?
That's a very interesting idea. You got a nice research paper there. I think it would definitely be something worth checking out. We will see that. So to evaluate and to some extent automate this second step, the iterative refinement of, tuning the parameters, oftentimes involves something called coherence scores, which do use, well, not GPT-3, but they do use, for example, word embeddings and other more recent techniques to compute a score of the quality of the topics and to sort of like give you a number that tells you how good are the resulting topics without having to read through all of them. If you have 200 topics, you might not want to go and read each and every one of them every time you change a little bit, but you could sort of observe the effect it has on a score. There are, ways to look at, for example, with GPT-3, I mean, language models, GPT-3 is a language model. A language model is essentially a black box that you can stick in any sentence, and then out comes a probability that says, this is how likely you are to encounter this sentence in the wild, right? If it's a sensible sentence, then this number will be higher. If it's a nonsensical sentence, this number will probably be lower. That's what language models originally were designed for. They were used to score the output of machine translation systems, for example, and then find the most fluent translation out of the possible outputs. But GPT-3 and other language models can also always be run in generative mode. So you can say, please just generate a random sentence that could occur in the wild. And that's how they're often used today. I think it would be possible to make use of that and like put that in this pink arrow loop to kind of assess the quality. Yeah, I think that's a great idea.
Thank you. And there's also another request from YouTube to post the links to some of the paper that you mentioned, maybe during the chat or during the break when you have time. Thank you.
Yeah, I'll post those during the break. Please remind me if I forget, but yeah.
We'll remind you. Thank you.
Okay. Good. So this is essentially the course of action. This is what we need to cover today, right? Like all of these different steps. So let's dive in. If you want to read more about this, I've published a textbook recently based on my the class I'm teaching on natural language processing. The first part is out on discovery and exploration, which does cover word embeddings and topic models, different types of topic models in depth. There is a second part that will come out presumably later this year, waiting on the proofs and corrections that will cover prediction and classification. I'm not actually making any money off of this, but if you're interested in having a textbook, then this is something I can wholeheartedly recommend because I know what's in it. There are also the materials for the class I've been teaching. I will post those later on a GitHub that also include lecture notes. So there's also some write-up of all this material in case you want to read something and you don't have access to Cambridge Elements. Most universities or many universities do have a subscription and you can probably access it through that, but otherwise you can use the free lecture notes that are available. Okay, there were questions.
Yes, Nader asked, do you have any recommendations for our implementations of the methods mentioned?
I don't know R too well. I know that one of the reasons why topic models are pretty popular in social science, and I should say they're probably more popular than you would expect them to be for something that is actually relatively complicated underneath and takes a lot of like computational tinkering. I think it's because, which you would think, is more like something that computer scientists are interested in. I think because they got popular because there is an R implementation that was very popular. I'm going to focus today on Python, which somebody asked yesterday, what would you recommend? I think R is great for a lot of things. It wasn't necessarily developed with text analysis in mind. There are a lot of good text tools, text analysis tools in R now, but it's sort of like a later edition. Python has a lot more native support for text analysis, and it is the language of choice in the natural language processing community. So everything I'm saying here in the theoretical part applies to any programming language that you have a topic model in. It's not specific to any language. But later in the notebook, we're going to look at a Python implementation, and I think for like performance purposes, like Python generally with text works better than R. I know that there is an R implementation of topic models and probably I know that there's also one for the structured or author topic models by Roberts et al. I can dig around and see whether I can find the link to that. Yeah.
Thank you. There were some more comments on suggestions from the audience on different R packages that they can use.
Okay, great.
That's it. Thank you.
All right. Okay. So let's back up. The topics we get are essentially lists of words, right? And what we would want ideally is a list of 5 words that very neatly describe a topic, so that when you give it to any reasonable person that is not out to make fun of you, and you show them those 5 words, they would say, ah, yes, this makes sense. This is topic X, right? So we really want to make sure that these 5 words that describe the topics are as free of noise as possible, right? And the most important step maybe in doing so is the pre-processing step. And this is also something we've talked about yesterday. So if you were present yesterday, then this will look very, very familiar. There are more questions or just comments on implementations?
Yes, it's just some more comments on the R implementations.
Okay. All right. So pre-processing in natural language processing in general is very, very important. When we get text, languages have different dimensions. One of the dimensions is information content. We use some of the words that are very important to convey the meaning of a sentence, but then every language also requires you to use certain words, certain constructions, inflections to make the sentence a grammatical sentence in that language. Those things don't necessarily convey that much information by themselves. And if you looked at just the word, if you just look at the word the, it doesn't tell you very much. It tells you it's a definite article, right? But that's about it. So if you have a sentence, let's say Obama met with Putin yesterday in Helsinki, and you wanted to condense the sentence to remember the fact, it turns out you could just remember the words Obama, Putin, Helsinki, and those 3 words would probably help you remember this, a week from now. Whereas if you used any of the other words, yesterday, in, with, met, those would not be super helpful, right? So not all words in a sentence are equally useful to convey the meaning. And this is the same for topic models. So what we want to do is really get rid of kind of the noise, the words that don't give us a lot of information. And with that, we really want to, throw out a lot of things. Topic models use something that's called a bag of words. They represent a document as counts of words. It doesn't matter where in the document, in a text, in a letter, in a tweet, the word occurred. It just matters for the topic model how often it occurred in there. So, because of that approach of topic models, we don't need a lot of these structuring elements of language like determiners, prepositions, personal pronouns, things like that, right? We also don't need all the inflections, so like he, she, it, goes, we're going, went, is going, things like that. We just can reduce all of that to the word go, so that's lemmatization. And really, we want to, make the input as uniform as possible. And we're going to talk about all of these steps here in more detail. We also want to throw out words that are too rare, because we don't want, oftentimes what can happen with topic models is that there's a topic that just contains rare words, but those rare words have no connection to each other. They just happen to be sort of the leftover bargain bin of topics. So it can be good to say, okay, just remove any words that occur fewer than 10, 20, 50, or even 100 times. And same, we don't want words that occur too frequently. So we can really also throw out, words that occur in more than 50% of the cases. In some cases, you can go down to 10% and say, don't use words that occur in more than 10% of the cases if you have a lot of repeat words. And sort of these early steps of like preparing my text and getting rid of noise words that might then quote unquote pollute my topics and make them less coherent, those steps are very, very crucial. And all of the other things we're going to do after this are going to have some effect on the composition of the topics and the number of topics, but the quality, the coherence, the purity, the interpretability of the resulting topics, the word lists, that is determined to a large extent at this stage in the pre-processing, in the removal of noise words. So pre-processing in general has the goal to remove any unwanted or not useful information in the text and reduce some of the variation in the text that is not carrying information and leaving us sort of with the core of what is useful. So oftentimes when we work with text, we have raw text that comes from the web, from blogs, from websites, from social media, and it often comes with formatting like this. There's like HTML formatting, right? And we want to get rid of those things and come up with a sort of core version of it. So the first thing we typically do is remove any formatting like HTML, XML, things like that, LaTeX, other things. Word of caution, oftentimes when people start working with text, the text for us is convenient to work with in Word or Google Docs, but those things are editors that are designed to be read by humans, right? So they have a lot of like formatting information, indentations, boldface, underline, font size. All of those things are less relevant to a computer, but they have to be encoded somehow. So if you actually look at a Word document, most of that Word document, most of the size of a Word document is not the actual text. It's all that formatting and meta information, but we don't need that. So for working with text, the best format typically is the simple TXT, unformatted, just plain text format. So we want to get rid of any of the HTML, other formatting. There are easy ways to strip those. You could also use regular expressions and things like that. We generally then want to split things into sentences, depending on what your unit of analysis is. If you work with topic models and you have an entire, let's say, political manifesto, then you might not need to split that into sentences. You don't care about where in the document it is in the end. You're just going to treat the whole document as one thing. And as I said, topic models treat documents as bags of words, so they don't care about the internal structure and where in the document the word occurred. They really just, reduce a document to words and the count, the frequency of that word in that document. Typically, though, we want to split things up a little bit. So we want to separate things like the clitic v of have off the pronoun. So I've becomes I and then space v. So basically, we want to insert spaces here to separate out the individual tokens, which will make it easier to treat individual words and like remove or keep individual words. So this is a step we typically do want to take. There was a question about this.
Yes, there are 3 questions. So we have 2 on pre-processing step. One is from Annalisa. Is there a way to express a risk factor from having cut too much meaning from the text by pre-processing through cutting out words like this?
That's a very good question. So I should say that I'm showing you kind of all the possible pre-processing steps you might not want all of them. Depending on what it is you're interested in, it might make sense to cut out certain things, but not others. We're going to look at the case of numbers, for example. In many cases, you might not be interested in the exact number. There's an infinite number of numbers. And keeping all of them might not be useful for many cases. In other cases, it might be very relevant that you know exactly what the number is, because there are only a handful of numbers you will encounter, and you know that when they occur, they are very important. So this is, again, this domain knowledge that you as the expert have to bring, and that you have to take into account when deciding which pre-processing steps to take. Because yes, if you use too many pre-processing steps and you reduce it too much, then you're throwing away useful information, right? So this step, as important as it is, it also does carry some risk for overdoing it. I'm not sure this can be easily expressed in like a factor or a number. Obviously, you can use things like the information content can be expressed in bits, or like, how much can this be compressed? I'm not sure that it would be a useful figure to have here in order to tell you whether you want to do it. Typically, what you would do is you would think about the logical pre-processing steps you'd want to take, carry them out, do your analysis, and then see whether you should always go back and look at your text and like, what does it look like after pre-processing? Has it thrown out some things that I think I would rather have in there? Or does it still contain some words that I think are useless and that I don't want? So, and if that is the case, then you want to go back and like rerun the pre-processing with slight changes. So this is something that there is no one size fits all. This is something that needs your human expertise and intuition. This is not a step that can be completely automated.
Thank you. And the second question on pre-processing is, what kind of data files could I use for pre-processing? So an example is PDF files for curriculums, for example. So what additional steps would I need to do in order to start working on all the steps that is outlined here? So it's something to do with OCR, I think.
Yeah. So obviously text files come in a huge variety of formats. Some of them are easier to work with than others. Generally, you want to remove all kinds of like formatting information. If things come in PDF, you probably want to extract the textual information and like save that as a TXT file. I know, I think Adobe readers and many others now have a sort of built-in OCR function that basically just recognizes what is text and sort of ignores everything else, and you can create a text-only version of the PDF. PDFs essentially being like pictures, right? And OCR, optical character recognition, again, also a natural language processing technique or machine learning technique, also builds on computer vision, that has made huge strides in the last few years and decades. So it used to be kind of useful, and now it's actually very, very accurate and very useful. There are also like free OCR programs available, and I know that, for example, for Python there are libraries to extract text information from PDFs and like put it into like an unformatted format. So I think one of the steps that comes even before this pre-processing is to take your text and put it all into the same bland unformatted text format, right? So you might have very different sources. You might have some things HTML tables from the web. You might have some XML files or SQL databases that you got. You might have some PDFs. And like one of the first steps would be to put all of that into the same format such that you can start the pre-processing.
Thank you. There is another question on pre-processing. So aside from describing running the model as an iterative process, would you say pre-processing is also a part of it? And would we go back to pre-processing step if not, we do not get what we want?
Yes, so the pre-processing is part of the pipeline. Ideally, you spend enough time already on the pre-processing and looking at the effects of pre-processing as we're doing now. I'll show you like the output of applying each of these steps, and you would want to do that to sort of like gauge already before you start running your topic model whether this resulting pre-processed text makes sense, and you'll develop a better understanding if you do this a couple of times. It is very important to still look at the data. So I know this is much more common in like social sciences and humanities, where people really work with text, with the data. I've seen workshops between political scientists and computer scientists where the computer scientists basically just opened their laptops and started like coding away to like process the text, and the political scientists like said, don't you want to look at the text first? And the computer scientist said, no, just I don't understand what's going on in the text anyway, so I'm just going to start processing things and then looking at that. But it is important to have this eye on the text, this human in the loop, even in the pre-processing step. That said, if you think you're satisfied with the pre-processing, you run your topic model, but then in the end you find out actually some of these topics contain words that make no sense. This is something that must have gone wrong in the pre-processing. Then yes, you might want to go back and like change that and remove those words by adding them to a stop word list, or maybe reduce the stemming lemmatization or whatever it is. Yeah, so it is definitely part of this pipeline.
Thank you. And the final questions come from Ibrahim regarding to the type of text that we can do topic modeling on. So what is a good way to perform topic modeling on short text? So I think this could be something like a tweet or a Facebook, for example.
Yeah. So generally, topic modeling is, doesn't have any restrictions on what kind of text you can work it on. It's a very good question, though. You will need to do slightly different things for shorter text versus longer text. We're going to talk a little bit about this. So there are some parameters in standard LDA, alpha and beta, that basically say how many different topics do I expect to see in a text document, right? If you have a long form document like a speech or a manifesto, that could cover conceivably 10 different topics, right? If you're working with tweets, an individual tweet will not have 10 topics, right? It has maybe 2 topics, right? And so you can control that with this parameter that we'll see in a later section of the theory, where you can say, okay, I think this is how many topics there will be in a single document. So again, knowing what kind of text you're working with will have that effect on later on. It will also affect the pre-processing to some extent, right? So you can be, if you have a very long document, you can be much more aggressive in throwing out words, right? Because there's just so much of it. If you have a tweet and you overdo the pre-processing, it could be that you're reducing the tweet to 0 words because you just threw out everything. So the size of your document, the length of your documents does have an effect, and you got to be mindful of that as well. Yeah.
Thank you. That's the last of the questions so far.
Okay, all very good questions. Okay, so we've taken our text, we've stripped. So first we've put it into like a text only unformatted format. Then we've removed any contained formatting elements like div or like HTML, XML, LaTeX. We've segmented the sentences. This is somewhat optional for topic models, but we've tokenized the words. So we've split off any punctuation into its own token, and we've split off any attached endings like v or nt, like didn't. right? Obviously, this is specific to English. You need a different tokenization for other languages. If you have some non-Indo-European, some Asian languages that, do not use this white space segmentation, where things are contained by the character, there it's sort of a slightly different task where you sort of like separate out the individual word parts or morphemes or characters to change those into context. But generally, you want to have a way that you could split a sentence on white space and end up with like each token, each concept as one element of the resulting list. Then once we got to this stage, we want to sort of we want to reduce the variation in the data. So the first one is typically that we lowercase things. That's just, oftentimes a good step. For topic modeling, that probably makes sense in most cases. We've talked about it yesterday for classification. If you're interested in classifying emotion or sentiment, then, seeing that somebody used uppercase to basically shout at somebody else online is useful information. So in that case, you don't want to reduce the upper lowercase distinction. For topic modeling, you probably don't need that distinction. I would think in 99% of the cases. So there, lowercasing everything makes sense. The same with numbers. We might want to reflect the fact that there was a number, but we don't usually need to know which number exactly, right? So typically what you would do is you replace each digit with 0, or sometimes people use a hash or some other symbol. That way you keep the shape of the number, but you don't have to store the individual number. Like I said, there's an infinite amount of numbers. If something has 4 digits, it's probably a year. If it has 2 digits, it's probably an age. If it has 2 digits and then a dot or a comma and 2 other digits, it's probably a price, right? Those things might be relevant for us, but that whether it costs $29.99 or $14.50, that typically, doesn't matter to us. So oftentimes replacing digits with zeros makes sense, especially in topic modeling. There might be cases where you're looking for, different years or something like that. And there's only like 3 years mentioned in all your texts that made huge differences if you look at historical documents, where you might want to keep those numbers. But in general, you probably want to remove numbers or reduce them to 0, but you could also remove them altogether. And then you want to probably reduce the inflection of words. So what is the inflection? Well, like I said, typically in many languages, you have to use a different form of a verb, depending on whether I do it or you do it or he, she, it does it, or they do it. English only, does this S at the end of the third person singular, he, she, it does. German or Italian or French or a lot of other languages require you to use a different form of the verb for each person, grammatical person. But that variation might not be useful for us. And so typically we reduce this to the lemma, which is the dictionary entry. So been, we would just reduce to be, did, we would reduce to do. So you reduce it to the word that you would look up in the dictionary if you wanted a definition of that word, right? There is an even more aggressive way of reducing this variation, which is called stemming, where you essentially snip off the ends of words. This is an iterative process of this. There are several language-specific rules, which says first remove any ed at the end of English words. If there's still an e left, then snip that off. Snip off any ing, snip off any this, snip off that, until you really reduce the word to, sort of the atomic core, to its stem that cannot be reduced any further because you've already done all the reduction steps. Those rules are specific to each language. The resulting core of a word, the resulting stem, might not be itself a word. It might be kind of, hard to read. You'd sort of still guess what it is and where it came from, but it's a useful way of reducing variation to an extreme. It can be worth doing it, but sometimes, you know, it sort of reduces things a little too much. So for example, it would reduce constitutes, constituted, constitution, constitutional, all to the stem constitute without even an E. It's just TUT at the end, which might or might not be useful for what you are investigating, but it's a most aggressive way of reducing variation. And lemmatization is typically the more sensible option, because we reduce variation that doesn't carry any meaning for what we want to do. Right? So we might not care whether you do or did something, so whether it's in the present or past, you just care about the fact that this action occurred at some point. There are a lot of words that we might not be interested in. These are called stop words. These are typically prepositions, pronouns. Prepositions is like in, of, over, about. Pronouns, he, you, me, she, them. Or articles like a and the, and other things like that. So they're oftentimes called the small words. These words typically serve more of a grammatical role. They have to be there to make a sentence grammatical, but they don't actually convey a lot of information in and by themselves. So oftentimes we just throw them out. There might also be words that are super, super frequent in your particular data set that you can just throw out because they don't, you know that they're going to be there. You don't need them to carry out your information. So if you work with party manifestos, right, every party is going to say, we, the X party, are going to do this, right? And you can always like cut out X party because you know the party that the manifesto came from, so it's not, you know, relevant information. Or you could replace it with a special token like party name. That is the same for every party then. You can oftentimes also reduce it to words of a certain part of speech, so noun, verb, adjective, adverb, and ignore all the other ones. So that's another way of reducing unwanted words. You need a part of speech tagger for that, but there are a lot of them available. For example, the Spacie library in Python has, you know, built-in very good, very fast pos tagger that you can use to, you know, throw out anything that's not within a set of parts of speech you're interested in. And then one of the last steps, and we're going to see this in the notebook, you want to join common expressions, collocations, words that typically occur together that denote just a single concept. So New York, we don't think of that as, you know, two parts. Yes, it's written in two words or two tokens, but really it's one quote unquote word or concept, right? Same with Los Angeles. The loss itself is not meaningful, right? It always occurs with the Angeles. So what we do is we typically just join them by putting an underscore between them. And so once we've gotten to this stage, we've sort of like, you know, thrown out most of the unwanted information, and now this is ready to be fed into our topic models. So basically what we've done is we've taken, you know, a text from the web with a lot of variation, a lot of kind of quote unquote useless information, and we've sort of stripped that off of all the fluff and reduced it to really just the core interesting aspects. And this is then treated as a bag of words. There's a question?
Yes, Nico has a question on, is there a general recommendations regarding the use of bi or trigram?
Bigrams are a good idea. There are some trigram collocations. You can achieve that by, in the notebook that I'll show you, you can run this phrase collocation finder repeatedly. The first time you run it on single words, on unigrams, it will, you know, join words together that are, frequently next to each other, so into bigrams. If you then run it again on this, it might join some of the bigrams together with other words into trigrams or even fourgrams. Typically, I think bigrams would be enough for most applications. It depends. If you have the World Health Organization frequently in your data, then obviously you'd want to, merge all of that together into a single token. But in most cases, we only want like 2-word combinations. But you can run it repeatedly and merge, 2, 3, 4, and more. Again, this depends on your knowledge of what kind of things you'll find in there. If you were working with data on the COVID crisis, right? World Health Organization and Center for Disease Control, those things would all, you'd probably want to have trigram collocations.
And a follow-up question says, would you use these for beyond collocations or for all words?
Oh, you mean representing the input as bigrams? Yeah. So this is a way of adding structure to it, right? By giving the model, instead of individual words, lists of individual words, you give it lists of bigrams or lists of trigrams. That is something you can do to add structure to it. People have experimented with it. There's a trade-off, right? Because if you add unigrams and bigrams and trigrams, then now you've created a larger vocabulary, right? But a lot of trigrams are going to be very sparse. They only occur once in a very large corpus. So again, you can experiment with that. From what I've seen, mostly it seems to be better to use unigrams, so individual tokens to give to the item, but join collocations. So if there are words that frequently occur together, those you want to merge. The others you probably don't want to merge because you want to keep the vocabulary of unique word tokens as small as possible. That typically gives you a better, crisper, nicer topic outcome.
Yes, that's it for all the questions so far.
All right, great. Okay. So now that we have that, we would be ready. So one thing that I've been made aware of is that yesterday we didn't take enough bathroom breaks. So, being mindful of that, I sympathize. My suggestion would be here at this point, we take a quick 2-minute break. So you can, refill your water or, take a bathroom break, also let it set a little bit. And then we're going to go back and look at the next steps of representing the text as input to our models. Sounds good? All right, see you back in 2 minutes. All right, welcome back, everybody. So let's dive back in. All right. So we've nicely cleaned up our text. And so now we got to stick it into our model. The way, and this has come up already, so some of you already are aware of this, is via n-grams, right? So typically what we do is we have a sentence that would be cleaned up already, and we will chop it up into parts. Those could be unigrams, which is simply every single word. Bigrams, combinations of two words where we basically slide a window of two words over the text and take a little picture of each combination of two. Trigrams, and then fourgrams. Sometimes people say quadgrams if they want to sound smart, but I think that's actually like a weird combination of like Latin and Greek that shouldn't happen. So typically people then say 4 grams, 5 grams, whatever. Right? And so this is typically the format that we use. This can, capture some structure in the text because you sort of see which words were next to each other in a 2 or 3 word window. And like I said, you can use that to add some information. On the other hand, you're adding more tokens to your vocabulary, and some of them might be very rare. So then, you're kind of like trading off some structural information for more quote unquote noise. The representation in topic models is called a bag of words. It's a bit of a funny expression, but basically it means like you're taking the you're taking the page and you're just dumping it out into a big bag, and like once it's in the bag, you don't know where on the page it was originally. It's just jumbled together in that bag. That's it. So the way this works is essentially you take a text and you just collect counts of each word. You take each word token. Each word token. There's a distinction between types and tokens. So tokens are the individual occurrences of words. Types are the unique different words that are in a document. So the sentence, a good sentence is a sentence that has good words. There's the word sentence is twice in there. The word good is twice in there, right? So all of these are tokens, but then we'd say the word type good occurs twice, right? And each of those occurrences is a token. So type is the set of words, and tokens are the individual words. It's the list of words. What we would do is we basically count the words, and for each word type, we count the number of tokens, the number of occurrences of that word type. And that's how we represent the sentence, right? And then typically this would be represented as a vector of words, right? Where we basically just say, okay, each word is assigned a position in this vector. Shakespeare is at position 1, and whatever else at different positions. And then we can basically represent each document as a vector where the number in that position tells you how often did this word occur in this position. And that is one way, a very simple way of having a uniform representation of all the documents in your corpus as a vector of a fixed length. So vector is like a list. So basically, once you know the vocabulary in your data, you have 12,000 words, right? Then you can represent each document in your corpus as a 12,000 dimensional vector. Each position in that vector is one word, and the value in that cell basically tells you how often did that word occur in this document. Obviously, most words do not occur in most documents, right? Some words occur very frequently, but most are, occur in some documents, but not in others. So these vectors would be extremely sparse, meaning a lot of the values would be 0. The word just didn't occur in that document. The problem with the counting approach is that just left to itself, we would end up with some words being very, very frequent and having high counts, and other words being very, very rare, right? This is something that occurred to this guy, George Zipf, I think in the 1800s or early 1900s, that, basically there are a couple of words in a language that are very, very frequent. They account for most of the words. If you just randomly open a book and you point at a word, there's a very, very high chance in English, for example, that it's the word the, probably the most frequent word in the English language, followed by a, and then in and of, and things like that, right? But then there are other words that, are very, very rare, but, very interesting. For example, platypus, right? Doesn't occur very often. And then, like words fall somewhere in the middle. The words follow this specific distribution, right? So the most frequent words are super, super frequent. The second most frequent word is a lot less frequent already. The third most frequent word is, again, a lot less frequent. And then it goes down from there. You see, this is like a steep declining curve. Also called a power law distribution or Pareto distribution. But in linguistics, when it comes to words, actually also holds for characters, also holds for syllables, also holds for morphemes and other elements of language. It's called a Zipf distribution in honor of this guy who found it. Same actually also holds for a lot of other things that occur in the wild world. City sizes in a country. There are some cities in each country that have a lot of people, and then the second largest city is typically a lot smaller, and the third largest city is a lot smaller than the second largest, and then it goes down, and then you just have a lot of cities that have, 10,000 people living there, right? So this is a very normal phenomenon. The issue is that, a lot of these very frequent words to the left of this line make up 50% of all texts, right? So if you took the 200 most frequent words and you colored them red, then that would be 50% of a newspaper if you opened it, right? And you just colored all of those words red. But unfortunately, those would not be the interesting words, right? Those would be the words like the, of, a, in, I, you, me, the stop words, actually the words that we probably removed, right? So having those words, pollute our data, and like even if we remove the stop words, there would be some words that are just super frequent, but that's not really interesting, right? If they just occur everywhere, they basically mean nothing, right? Because they're just, yeah, like the air, right? You don't know that it's there. So what we want to do is kind of like, instead of using the raw counts of the words, we kind of want to give them a weight, an emphasis, an importance factor. And this is the TF-IDF, or term frequency inverse document frequency weight. If you have a bunch of documents, some words occur everywhere and they occur frequently in each document. Those are not very interesting words like the, but there are some words that occur rarely, but if they occur, that's actually that's something we want to notice. So the word sustainable, for example, right? Those words stick out. They kind of are more interesting in a way. And this goes back to early research in information retrieval, information extraction. So the early days of the web, or like even before we had really the internet, people wanted to retrieve information from large amounts of text, library systems, and catalogs and other things like that. And one of the people working on this was Karen Sperk-Jones, one of the pioneers of information retrieval. She, first became a teacher, then decided she doesn't like teaching very much, and that was a good thing, because then she decided she's going to do a computer science degree at Cambridge in England. If she hadn't done that, then we probably wouldn't be sitting here, because she invented a lot of the things with TF-IDF and other contributions that now are used standardly in search engines, in NLP, in text classification, in topic models. So that really laid the foundation. She was also a ceaseless campaigner for getting more other women to join computer science, which is a noble cause because still a very imbalanced field. And in her honor, there is a computer science prize that people can be nominated for. So if you ever meet somebody who has a Karen Sprague-Jones Prize, they probably did something smart. So thanks, Karen. What she did was basically to say, well, okay, so words follow this distribution. There are a lot of like frequent words, but they don't mean anything. There are a lot of these other words in the back that are rare, but probably we want to use them. But she had an intuition that there's different ways of looking at these other than just the raw frequency of the words. So I said earlier that in our bag of words distribution, right, we can represent each document as a vector of counts, right? So each row in this matrix X is a document, and each column, like here I marked a column, is a specific term or word, or could be a bigram or a collocation or whatever, right? Let's say this is the one for platypus, right? You can look at this and you can look at the individual documents in which it occurs. Those are the blue cells with a number in it. So those documents have the word platypus in it. And you can just say, okay, in total, in my entire corpus, how many times have I seen this word? Okay, 9 times out of all of the words in my entire corpus. But I can also look at how many documents, different documents has it occurred in. And here that would be 4, right? So those are different ways of looking at the same column, at the same document. In one case, we're just summing up the numbers in that column. In the other case, we're counting the number of non-zero cells. One is the term frequency. How often do we see this term in our entire collection? And the other one is the document frequency. In how many documents do we see it? The inverse document frequency is essentially dividing by the document frequency, but for computational efficiency reasons, typically we would just take the number of documents and then divide by the number of documents that contain this word, which roughly amounts to the same thing. And we can then multiply that with the term frequency. Because those numbers can get very small, we typically take the log of things. So the log is a squashing function that makes small numbers a little bit bigger and large numbers a bit smaller, so that they're all in a more reasonable range and you don't have like huge outliers on either side. And if you put this together, essentially we're dividing the number of times we've seen a word in a corpus by the number of documents it has occurred in. And it turns out if we do this, then we actually get a new value for each of the words. And we can basically represent it by that. And it turns out that the words that are frequent and actually occur everywhere, they get a very low number because they occur in many documents. So we divide by a large number. And the words that occur only occasionally in some documents, they get a much higher number. So using this actually can sort of weigh the influence, the interestingness of words much better. And this is what we use in topic models to pay more attention to the words that we want to use. We can plot this. So here, I've done this for the novel Moby Dick. We can plot the inverse document frequency of a word against its TF-IDF value. And then the size of the bubble is the term frequency, so how often the word occurs. And you can see that the top words in Moby Dick are about, it's old-timey sort of seafaring pirate speak, yay, or instead of you. There's a lot about chapters. This is just a function of like the book being very well structured. And then it's a lot about whales. Yeah, it's a book about whaling. And it's a lot about man as a, abstract concept, like, what is man? What a piece of work is man. And it's about this guy named Ea. So we can, sort of plot this and look at it and, sort of see, and this is also a good way of analyzing a text and kind of getting a sense of what this is about. What are the important words? But more importantly, this is a good way of representing our text. So we now have each document represented as a vector. Each position in this vector stands for a particular word, and the value in that cell is the TF-IDF weight of that particular word in that particular document. And so a higher number means this is an interesting word, please pay attention to this model. And a lower number means you can, maybe you want to use this, maybe not, right? So this is a good way to represent what we want to pay attention to in our models. And so now that we have that, we are actually ready to get started on learning topics. Questions up to this point?
No questions for now.
Okay. All right. So we've taken our documents. We have removed all of the fluff. We've sort of pre-processed it in a nice way. We've reduced the variation. And then we have represented each document as a list of as a vector of the words and their TF-IDF weights, right? And this is now what we give to our topic model. In this case, latent Dirichlet allocation. This is the first probabilistic topic model as it has become famous and like ubiquitously used. Now, so as I said, there were other types of topic models before that basically use dimensionality reduction, but they're a little bit less flexible and they're not very text specific. So you could use those techniques also on survey data and other things. And in fact, that's how they are used to sort of identify user groups and other things in like consumer research and others. You could use that also on text data, and it's kind of okay. It gives you some sense, but it's not as, you don't have a lot of influence if you don't like the output. So with those, what you get is what you get. With topic models, you can use a little bit more of your intuition about the text to put in there with probabilistic topic models like LDA. Now, one thing that we need to sort of understand about topic models, though, is that topic models are text specific, but they basically say, look, I think there is a specific way in which people generate text. So the text that I'm seeing as a topic model has been generated by a certain data generation process, which I'm going to go into in a second, which is a little bit weird. It doesn't make much sense. It's not how actually documents are created. But by making this assumption, like this is how people generate text, we can essentially reverse engineer that process and then go back to the underlying topics. Because, and bear with me here, this is going to be a little bit weird. Topic models say, okay, in order to get a document, here is what occurs, here's what happens. Yes, there's a question.
Yes, there is a question. Someone missed what the N in the IDF formula on slide 27 means.
I think in that case, the N is the number of documents in the corpus.
Thank you.
Yes. Okay. So topic models say, all right, assume that this is how documents are created. And if we assume this, which is a bit of a weird story, but if we assume that is true, then I can reverse engineer it. And that means I can tell you the topics that were in there. So here is what LDA thinks happens when somebody sits down to write a document. So first, that person says, okay, this document is about, we have 5 topics, and those 5 topics are going to occur in these proportions. So the third and fourth topic occur around 1/3 of the time. So 1/3 of the document each is going to be about the yellow and the pink topic, the third and the fourth topic, and the other ones are about the first, the second, and the fifth topic. So this is sort of the composition. This is the overall topic distribution of this document. This is what this document is about. Now that I've decided this, I will go through each word in my document. Let's say I want to write 500 words on this page. And so for each word, I will draw a topic from this distribution up top here. So I'm going to reach into this distribution and draw out one of the topics. And, because I do this repeatedly, that will roughly follow that distribution that we see up there. So I'm going to draw a topic, and I draw topic number 3, the yellow topic. Okay, good. So the first word I will put on this page is going to be a yellow topic word. Now let me draw from a distribution over all my words in the vocabulary, a word from the yellow distribution. Okay, let's take this word. All right, now I'm going to write this word onto the page. Okay, now I've put one word onto the page. Let me repeat this process. I will draw from my topic distribution. I got the topic number 4, the pink topic. And now I will randomly draw a word from the distribution over all the words in my vocabulary in the pink topic. And I'm going to put that on the page. And then I'm going to do that again and again and again and again. And I'm basically just going to start filling the page with this weird drawing process that is based on the distribution of topics in this document. And then once I've reached the end of the page, that is how this document got created. And then that document goes out into the world. Now, very obviously, this is not how anybody writes a document, right? This is an oversimplification of what is happening in the creative writing process. But the thing is, if we accept this weird story as the origin story of how documents got created, then we can reverse engineer it. And we can say, okay, I will take this document. I will now have to figure out which topic each word came from and what the distribution over words was in each topic. And then I can, sort of like reverse engineer all of those things. And then I can learn the distribution over for words over each topic and the distribution over topics for that particular document. So I can learn Z. This is the left on the lower left-hand side, the distribution over all the words in my vocabulary for each of the different topics. And I can learn theta, which is the bar graph on the very top, which tells me this is the proportion of each topic in this particular document. I assume there are questions.
Yes, there are several. One is, can LDA be performed on TF-IDF values?
Yes, absolutely. Yeah, should be. It should even be performed on TF-IDF values. Mm-hmm.
Then the next one, how do we get the initial topic distribution list?
Very good question. Random. So
okay, that was
yes. So essentially, so this is an unsupervised learning process, right? So all we see is essentially this document at the bottom of the page, right? But we don't know what the color of each of the words or which topic each of the words came from. So essentially, we're telling the model, look, here's the story of how the words got on the page, and here's the page, right? Here are the words. So now you can like noodle around these these two probability distributions, the underlying distribution for this document, theta, and the distribution over words for each of the documents. And you can like try out any combination of those two until you get a satisfying explanation of this particular document. And we're going to do that for all the documents in our data. And obviously, so theta is particular to each document, but Z is shared between all of the documents in my corpus, right? So the topic model needs to find a distribution over words for each of the topic that makes sense for all of the documents. And then it needs to find a distribution theta for each document that together with Z makes sense for the entire corpus. But essentially, we start out randomly and then work from there. we're going to see that in a few slides. It's called the expectation maximization algorithm.
Cool, thank you. So there is a couple more questions.
Yeah.
First is, do you draw the most frequent word within each topic or any word?
You're going to draw from that distribution proportionately. So what that means is, if you drew 1,000,000 times, then you would draw the most frequent word most of those 1,000,000 times, right? And the least frequent words you would draw least frequently. But you draw proportionately from those distributions. But yeah, you don't always just draw the most frequent word. Otherwise, it would be, a very repetitive document.
Then the next question, how does the model define the topics? Apparently, the positioning of words doesn't matter.
Yeah. So this is the question, right? So by varying those two parameters, theta and z, the model needs to find a in itself coherent explanation of the data that we've given it, right? The data is the data. Like, the documents are unchangeable, right? The model cannot change the words in each of the documents, but it can change theta and it can change z, and it needs to do that until it can explain the data that we've provided it with, right? And so by changing those parameters, right, the model can decide, oh, actually, I can explain all of the documents much better if I say this word is, a word from topic 1 rather than from topic 3. So let me reduce its probability to occur in topic 3, and let me increase its probability in topic 1, right? And that way, it sort of, by doing that, it kind of groups words together into topics, right? So all the words that have like high peaks in the on the lower left in the Z distribution, for the blue distribution, those are, all the words that are particular to topic 1, right? And those words are sort of defining topic 1. Note that each word has a probability for each topic, right? So each of those bars in the lower left occurs for the first topic, the second, the third, the fourth, and the fifth topic, right? But it has different heights for each of those. So there is one word, let's say the word Australia, that's this the big blue bar in the first Z. That word, right, occurs a lot in the first topic, but it's it's much less likely to occur in the second or the third, the fourth, or the fifth topic. And sort of simply by moving those probabilities around until the model can explain the data, it implicitly creates these groupings of words together into topics.
And the last question, so the initial list of topics needs to be exhaustive, correct?
I'm not sure I understand that question.
It might have been like a follow-up question for the previous conversation. I'm sorry about that. But if the author can maybe like write in the chat more explicit what they want to ask, we can repeat this question later.
Yeah, this is Ashima. The question actually was a follow-up. So you mentioned that the initial list of topics is random. So my question is, the list of topics that I select, so that has to be pretty exhaustive, right? I mean, if I miss out any topic, then it's not going to be in the final model that comes out. Is that a right understanding?
Yes. Okay. Thanks. I think I understand better what you mean now. So exhaustive sort of kind of implies that we kind of know what the full range is, but we can't necessarily know that a priori. However, something you have to decide, and we're going to talk about this a lot in the next few slides, is how many different topics are there, right? So here we have decided that there are 5 topics that exist, right? But maybe we can get a much better explanation of our data if we use 10 topics or 50 topics, right? And so choosing that parameter, like how many topics are there, that is the important one for like getting a good fit and a good explanation of the data. But doesn't, independently of how many topics you choose, the model will always find some explanation of the data. Some of them will be better than others, but the model will always converge to some explanation, right? Which might or might not make sense to us as human readers.
Okay, thank you.
No more questions for now.
All right. Okay, so this is super weird, and I'm fully cognizant of this. The first time I read this, I was like, what the hell? Like, who came up with this idea? I mean, Bly et al. Came up with this idea, but it's kind of like a weird way of thinking about it, right? And it's kind of surprising that that actually works, and then in the end results in topics that we can look at and interpret as coherent topics that we would be able to put a label on, right? But because of this property of language, of the distribution of words following a Zipf distribution, and because of these latent topics that sort of come through in documents, and because of these 2 parameters that the model can play around with until it's satisfied, it kind of works in the end. But, and this is the big but, this is not deterministic, right? Depending on how I said we start out randomly, and then we keep tinkering and like changing that theta and changing z until the model reaches a stable configuration. The model will always reach a stable configuration, but it will not always be the same stable configuration, right? So if you run a topic model 10 times, you will get 10 slightly different solutions, 10 different topic distributions. And some of those topics will be stable. They will occur 10 times. Others will only occur in some of those solutions, but not in others, right? So this is something to be aware of. Like, you cannot run a topic model once and then basically assume that, if somebody else redid it, they would end up with exactly the same topics, right? And it is for that reason that you can never, ever use the output of a topic model as input to a regression or classification model. That you're basically using random numbers to some extent as independent variables as input to a regression model. So if you ever see that in a paper, please reject that paper and send it back and tell them this is what you're doing makes no sense and it basically is irreproducible. Unfortunately, this is fairly common. But yeah, because of the stochastic, the random nature of topic models, you will never get exactly the same solution twice if you run the model several times. One thing you can do is you can set a random seed so that everybody starts with the same random distribution. But other than that, yeah, like it's not deterministic. Was there a question?
We have a couple questions. Yeah. Well, I don't know. Johannes, I guess your question was just addressed, but I will ask it anyways. Does the same model give different results or only if you change the parameters?
No, even if you use the same parameters, so same number of topics, same alpha, same beta, which we haven't talked about yet, but we will in a second. You keep those the same. You run the model twice with different initializations, and you will end up with similar but slightly different solutions in the end. Yeah.
And there is a couple more questions on YouTube. So how do you decide how many groups to use? Is that trial and error then?
Yeah, we're going to talk about how to do that, and I'm going to also then show you the code how to do that. So this is a parameter that you need to choose, and some of them will be better than others. Obviously, we need an automated way to measure better, right? We cannot, if we want to try 10 different number of topics, we cannot like run a model and then read through all of them each time and sort of decide whether this one is better than the other, and if it was not, we have to go back. So there is an automated way to do this, and we're going to look into this in a bit.
And actually, a couple more questions popped up. So you can still have the LDA result as a dependent variable as in structural topic modeling, correct?
No, so structural topic modeling is a variant of LDA that uses another, it essentially uses another constraint on the model. So you say, okay, here's how a document is constructed, but I happen to know that this document comes from the US, and like there's another document from Italy, and there's another document from France. And I suspect that that means my distribution over topics is going to be slightly different in those different countries. So the structural topic model essentially says, it adds another parameter to the model and says, I know something about this document. And like, when you find an explanation, dear model, you will have to take this into account. So you have to explain the fact that, there are a different prevalence of topics in, let's say, the US, Italy, and France. So it just adds another thing. It's not a predictive model.
Okay, and we have two quite similar questions on Zoom and YouTube. I'm going to just read them together. So one, should you run the model several times then and search for stable topics, or are there differences, or are the differences so minor that it suffices to run it once? And a quite similar question, is it useful to run the models n times with different initializations to check which topics are the most robust?
Yeah, so those are good questions. It is good, good etiquette to, good practice to run once you're satisfied with the number of topics and the parameters, to run it several times, just to get a sense of like what of this is stable, what of this is invariant, and what of this changes a little bit from run to run. And it's interesting, you'll see that there are some things that never change, right? There's always come back. There's always this topic about food, right? But there are some other topics that sometimes occur and sometimes they don't occur. And so obviously, you can then say, okay, this food topic I can be very confident in. However, even that food topic, which is described by, let's say, 5 words, the order of these words might sometimes change, right? So it's not always the same order of words. So, and again, also because the assignment is random initially, sometimes the food topic might be topic 3, and sometimes it's topic 10, and sometimes it's topic 1, right? So that will also change. But so that's why you also always need this human in the loop and this analysis and this feedback loop of, oh, what is the output? Does this make sense? What is stable? What is, what is changing?
There was a question, but I think the person responded to. Okay. I guess it was interaction with me. Sorry. So Marcus is asking, if you evaluate your topic model well, why shouldn't you use it in a regression later on? For example, in a time series model for the temporal development of certain topics. And then yeah. The same person says that if someone does STM, I guess you basically set the desk project papers that do that. I don't know.
Yeah, essentially, I stand by that because it's not reproducible, right? And so if I publish something, I have an obligation to make my results reproducible. But if my topics keep changing every time, and I cannot give you the exact, I cannot expect that you will get the exact same distribution over topics, right? And your topic number 5 will not be my topic number 5, and the like the same composition will not be exactly the same, and the proportions will not be exactly the same. If you change the inputs to those regressions, like I will not be able to reproduce the regressions, right? And so I cannot be convinced that the results you're getting are generalizable because they will not reproduce.
And a couple more things. Why would the topics change even if you're setting a seed?
If you set a seed, they don't. If you set a seed, they typically stay. Yeah. So that's a good way to reduce variation. The thing is that the seed, so random number generators are like a huge topic. It turns out it's actually really hard to be really random. And a lot of research has gone into like how to make truly random numbers. But then also you want to make that reproducible. The thing is, like, even if we use the same random seed, we might still get slightly different output because the way that random seed is used to get random numbers off of the processor or the internal clock or whatever it's using might be slightly different, right? So it is very hard to get truly random numbers, but then also make them, the same for everybody.
Yeah, no more questions.
Okay. All right. So before we move on, where are we? Okay, we have a document. We've cleaned it up. We represent it as TF-IDF values. Then we accept this ludicrous promise that, this document was represented by somebody drawing a topic distribution for it, and then according to that topic distribution, drew each word from, one of those topics and put it on the page. And because we accepted that, we can now reverse engineer that process. And that means we now have a distribution over all the words in our vocabulary for each of the topics. And we have a distribution over topics for each of our documents, right? So we can run this process. In the end, we end up with theta for each document and a z for our entire corpus. Okay, and there's a lot of randomness involved, and we should run these things repeatedly and look at the output it produces every time. Okay, so this is what we get, right? So this is the theta, which is the probability of seeing a topic given a particular document, right? So we have one theta for each document in our corpus, right? And here are some random examples of what that might look like, right? So document 1 is predominantly topic 4. Document N is predominantly topic 5 and nothing else, right? And some others are more mixed. Z is another conditional probability distribution, right? Or multinomial, which basically says, given that I have a certain topic, let's look at topic 1, what is the probability of seeing word 10, right? And I can just look that up and read off the probability. So this is essentially, again, like a matrix, right? So each word is one column, and then each row is one topic, and the value in it is the probability of seeing that word in that particular topic, right? And this Z parameter is shared across all of my documents in the entire corpus. And yeah, in order to describe a topic, essentially what I will do is I will look at the, say, 5 words in my topic distribution Z, and like return them in descending order of probability, right? So I would choose those 5 words that are marked here with the arrows, and in the order, descending order of probability. Those are my topic descriptors. That is what topic 1 is about. when you read papers about LDA and about other topic models, you will often see plate notation, which is variants of this. Some of you might be familiar with this, so this would be repetition, but for many this might be new, and it can be a little bit confusing. What does this mean? So we got a bunch of elements here. We got circles, we got squares or plates, and then we got these like rounded squares. And then we also have like a shaded, so grayed or clear nodes. And all of this, has a meaning. So if you understand this vocabulary of graphical plate notation, then you'll be able to understand the structure of these models. Okay, let's go through. A square basically means whatever is inside of this should be repeated, right? So here we have one plate for the number of documents. So we're going to repeat things for each document. Everything that's inside theta, z, and w gets repeated for each document, right? We have another square inside of that, another plate, which is the number of words. So these are the words in a document, and everything inside of that gets repeated for each word, right? So now, you can sort of see, because we might have, a large number of documents with varying number of words, this way of showing it basically abstracts away from these differences and then essentially says, okay, for each document, you have your own theta. That's why theta has this I subscript. And then you have a certain number of words in that document, right, which has the subscript j. And so, for each word, I will, I have a z value, and dependent on that, I have a w value or a word. Theta is the topic distribution, which is specific to each document. That's why it's in this outer plate of the documents. Right? Z is the word distribution, right? And so I have for word J and topic I basically have a specific word or a specific probability. And then I have these hyperparameters, beta. So this beta is, like influencing the word that we see. You see that the round node, so round nodes are random variables. The rounded squares are hyperparameters. And the gray node, the W node, essentially means this is an observed node. This is given. This is not something the model can set. This is something that it has to accept as is, right? And so this beta parameter together with Z influences the word that we see on the page. So beta is basically a parameter that controls how specific are words to topics, and like are there certain words that only occur in one topic and then it never occurs in another topic, or are there words that can occur in 2, 3 topics, or maybe in all topics? In all topics wouldn't make sense, right? But maybe there are words that belong to more than one topic. We can have that, and we can control this gradient sort of with the beta parameter. And we have another parameter alpha, which says how many different, and this controls the theta of each document, so the distribution over topics for each document. And it says how many different topics do I expect to see in my documents, right? And this goes back to a question we had earlier. If I have tweets, well, I'm probably only going to have 1 or 2 different topics in a tweet, because the tweet is so short. So there's not really that much I can talk about. But if I have a long form document, maybe I expect that to go about 5, 10 or more different topics. And so this alpha is how I can kind of nudge the model into that direction. So I should note, this is not a hard and fast restriction. This is a hyperparameter. So this basically just encourages the model to search in that direction. And you say, I think there's only going to be few topics per document, or I think there's going to be words that are specific to maybe 2 or 3 topics, but not more, right? And that sort of like nudges the model gently in that direction. It's not like a hard and fast rule or constraint. There are some questions?
Yeah, there was a discussion, I guess, about like desk projection of papers was using topic models as a dependent variable, I guess, but no explicit question. So I'm just gonna leave the discussion there, and if authors want to, talk to you about it, they can do it later.
Yeah. Okay. So yeah, these are the hyperparameters, and these are sort of like, gentle suggestions to the model. And so this is the plate notation. We're going to get back to this with the author topic model later on. You don't have to learn this by heart, but maybe now it makes a little bit more sense. And if you come across a paper with LDA or other topic models, or there are, like a whole class of models that use this, probabilistic models in general, that use this plate notation. So both alpha and beta are essentially parameters in a Dirichlet distribution. What is a Dirichlet distribution? Well, a Dirichlet distribution is essentially a distribution generator. And it takes 2 parameters. One is the number of different elements, for example, topics, or words. Some of this is labeled word here. I apologize for that. So we have like a green, a yellow, and a purple, word 1, word 2, or word 3. And so a Dirichlet generator basically says, okay, I will generate distributions over those 3 elements with different ratios, with different proportions. And the proportion between these 3 elements are controlled by a second parameter, which is in the Dirichlet function called alpha, right? And so this is what we use. If we set alpha very low, and this is the left graph, we basically say, out of those 3 elements that we have, one is going to be dominant and basically account for 100% of the distribution, and like everything else is essentially 0. And if you look at the left one, basically these are 20 draws from a Dirichlet with alpha 0.01 and 3 elements. And you can see most of the time it just has like 1 element, just word 1 or word 2 or word 3, and nothing else. The only exception is draw 16, right, where the word 1, the green one, has like a little bit of probability, but everything else is the yellow word 2, right? So this generates distributions that are very, very skewed, very, very, 100% one thing and nothing else. So this is like an either or distribution. If we set alpha 1, we get the graph in the middle. So this basically says we have something that looks a little bit like the Zipf distribution, or the Pareto power law distribution, right? Out of our 3 elements, we have 1 that is dominant, and then we're going to have 1 that is, a lot less likely, and then we have 1 that's, like the least likely, right? And it's sort of going to fall pretty quickly. So the most frequent one is much more likely than the second most likely one, and that is going to be more likely than the third most likely one. So if you look at each of these draws from top to bottom, right, each of those has like 1 dominant word, 1 dominant element, and then the other 2 are less likely, but it's not as skewed, not as extreme as on the left when we set alpha to 0.01. And if we set alpha to a higher number, like 100 or 1,000, we approach a uniform distribution over our elements. You can see that here there are some differences, but largely, it's like 1/3, 1/3, 1/3, or close to uniform, right? And so this aspect of alpha, this alpha parameter of Dirichlet distributions, that is what our hyperparameters in the model control, right? And so what does that mean? Well, for alpha, remember, this is the number of topics we expect to see in a given document. Choosing a very high number, like 1,000, means I will see every document, every topic in every document. It's a very uniform distribution, like all documents contain all topics. This could be, for example, a bunch of party manifestos. They're all going to talk about all of the topics in a given election cycle. If I set my alpha very low, I say this is very peaked. There's going to be one dominant topic in a document, and everything else is probably not going to get mentioned. So there's like one or two topics at most in a document. This is when we have tweets, for example. We want a very low alpha. Same holds for beta, the beta parameter. If we set it very low, then that means each word is going to be very specific to a particular topic, and it's only going to occur in that topic and not in other topics. This could be, right, if we have very highly specialized topics that are mutually exclusive. But, if we suspect that, there are topics that are so similar that they will share some words, then we probably want to set a higher beta, right? Up to 1,000, where basically all words are equally likely for all topics, which I've thought about this a little bit, but I couldn't think of a situation where that would make sense, that then you basically don't learn anything. If all words are equally illustrative or indicative of each topic, then there's really no distinction between the topics, right?
Here's
Okay.
the question.
Yeah.
So the question, I'm getting a bit confused with the differences between respectively theta and alpha on one hand and a z and beta on another hand. Both are some sorts of distribution of words/topics.
Yeah. Okay. Good. Okay. So here is the topic model in the end has two parameters that we need to learn, right? So what we have is a whole bunch of documents, and the documents are what they are. And we say, look, I think there's 5 topics that can explain all of the documents in my corpus, right? So I have my documents and I say there's 5 topics. And now what I need to do is I need to find a theta, like a distribution over topics for each document in my corpus. And I need to find a distribution over words for each topic, which is Z, which is common to all of my documents, right? Those are parameters I need to find. And this is what LDA does for me, right? LDA says, all right, you want me to find theta and Z for you, given 5 topics and these documents. Let me run and I'll come back to you. And then LDA basically says, voila, here's your theta, here's your theta that I found for you after fitting on the data, and here's your Z for you that I found after running on the data, right? And you say, okay, thank you, that's what I wanted. Alpha and beta, respectively, are ways for you to influence LDA in finding theta and Z, right? So you can say, okay, dear LDA, here's my corpus of documents, and I think there's 5 topics in there. I also happen to think that these are tweets, so each document is only going to have 1 or 2 topics. So I'm going to set my alpha very, very low, 0.01, right? So when you draw your thetas from a Dirichlet, you will draw very peaked distributions for each document, right? You're going to have a very peaked distribution over topics per document because you're drawing them from a Dirichlet distribution that is very peaked, that has like 1 or 2 topics and nothing else, right? So out of my 5 topics that I tell you are in there, each document is going to have 1 or maybe maximally 2. I also happen to know that these are highly specialized, mutually exclusive topics, like it's cat food, healthcare, rocket science, religion, and sports, right? And these have nothing in common. So if you see a word, then it basically can only come from one topic, but not from another. So if you see pet, it cannot come from sports or rocket science or healthcare. It can only come from cat food, right? Based on that, I will set my beta very low, which basically means all the words occur in one topic, for one topic, but not in other topics, right? And so now you say, okay, LDA, here's my data, here's my constraint. I want you to find 5 topics, and here's the alpha and the beta, which means I want very peaked topics. I want 1 or 2 topics per document, and each word should be indicative of one topic, but not more, right? Now go and find a solution for me. And then, LDA says, all right, I'm going to go and check this out. And then it comes back and gives you the solution it has found under those constraints. Does that make more sense?
There's well, someone in the chat on Zoom says yes, but yeah. There's also another question. If you cannot trust the models for a regression model, why trust them at all? Yeah.
So I think this is something that has always puzzled me a little bit, that people assume because it's a statistical model, it can sort of uncover the hard truth, right? But I think if you take anything away from today, I think it's the fact that topic models can help you make sense of large amounts of text, but they require interpretation, right? And they're not, their interpretation helps. They're not an interpreter, right? So they don't do all the work for you. They help you systematize large amounts of text and make them more manageable by breaking them down into smaller underlying latent dimensions, topics, but they will not explain to you everything. They do require you to take good care in the run-up to like what you feed the model, but they also require you to take a look at the output and decide whether this is sensible and whether this is trustworthy. But then it can actually tell you things, right? So if you set everything up, you run your model 3 times, 5 times, and you see there are these stable topics that pop up again and again and again, and you realize, oh, in my corpus of I don't know, like government hearings, there is this repeated topic of childcare, right? Like this is not something that was known a priori, but this is a stable topic that pops up again and again. So now that tells me I need to be aware that childcare actually is a prevalent topic in this corpus, in this data set, right? So this is the insights that topic models can generate. They can help you structure and better understand large amounts of text. Or as another example, we collected a large corpus of tweets related to the pandemic, to the COVID pandemic in Italy. And we wanted to then go and label each of these tweets with the emotion expressed, but also the general theme or area. Is it about sports or politics or economics or something else? And so what we did first is we looked at a couple of tweets by hand, right? Just got some and said, okay, emotions, we have like predefined emotions, the Plutchik emotions, so we can use that. We don't know what kind of themes there will be. We're pretty sure that there's going to be something about economics, right? Loss of income, things like that. We're pretty sure that there's going to be things about politics, restrictions, lockdown, blah, 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 blah. There's going to be something about health. And maybe there's, something about sports or entertainment, right? Like Serie A closing down and things being delayed. but there might be other things that we're not aware of. So we ran, topic modeling on the entire corpus of like 6 million tweets that we had at the point. And that came back with several stable topics where we realized, oh, there's also, a sub-theme in here about vaccination, hesitance, anxiety, or whatever. There's also a stream of conspiracy theories in there, right? So 5G and other things that showed up. And so, running these topic models then allowed us to define the categories that we would, annotate the data with. So this helped us to understand this large amount of tweets that we couldn't, exhaustively analyze by hand. So that is something that topic models absolutely, facilitate and help you with, but they don't, do all the work for you.
There is another question that asks if LDA could be related to a qualitative type of analysis.
I mean, in my mind, it kind of is a qualitative type of analysis, because it does require interpretation and it does require this domain expertise, right? It's a little bit like a funnel or a filter that allows you to sort of, get a handle on large amounts of text that you couldn't do manually. So it is a quantitative method or a quantitative statistical model, but I think it mainly facilitates a qualitative analysis. So I think oftentimes people see a dichotomy between qualitative or quantitative, and these are, like either or, these are exclusive. To me, these are mutually informative. And I think LDA and topic models are actually a great example of that. You have a quantitative approach to the data, which allows you to do better qualitative analysis, which can then go back to inform your quantitative model and refine it and make it better and give you more qualitative insights. So to me, these two are, two sides of the same medal.
There is another question of Johannes. If you are interested in something like Marcus mentioned before, development of relevance of certain topics over time, would you rather use word count data? I imagine something like finding climate change related words via topic model, then count these climate change words or climate change words document ratio and analyze them over time.
Yeah, so there are different approaches. So you can use, we talked about this a little bit yesterday, word embeddings, and you can sort of like have them on different time slices, and you can see how the definition, the associations for a particular word change over time, right? So like, I'm making this up as we go, right? So you take the Google Books corpus and you look at the associations with green from 1900 to 1990 or 2000, right? And you would see how there are different associations, different semantic fields associated with the word green, right, in those different decades. You could set it up as a, I'm not saying you shouldn't use topic models for these things. You could use like an author topic model where your covariate is the time step, the decade, for example, or the year, right? And you would say, I expect there to be a change in the prevalence of certain topics over time, right? And so that would be one way to approach this.
There are no more questions.
All right. So it's 12:10. So I think, this is a good time to take our 15-minute break in the middle, get a coffee, get some water, get a snack, take a bathroom break, and then come back in 15 minutes, so 12:25. And then we're going to talk about the training and parameters. How do we choose? How many topics are in there? How do we choose alpha, beta, and so forth? And then, once we're through with that, we're going to go and look at the notebook. again, like yesterday, I would rather spend more time on this first part of the underlying theory and the understanding what's behind it, because in the extreme, you could run the Colab notebook yourself. It has explanations in there, and you could sort of see and understand what's going on without me necessarily explaining it. But here, these things, I think, and the discussions around it are the more useful part at the beginning. So I'd say 15 minutes, and then we see each other again, 12:25. All right?
And it would be great also if you could post the links to some of the papers that you mentioned.
Excellent. Thanks for the reminder. Yeah. Yes, I'll post those. Hello, welcome back, everybody. All right. So I hope everybody has had a good break. I'm going to say a couple of things so everybody can, like, slowly ease back in. So over the break, I posted some links. One is a link to this paper that I mentioned by Boyd Greber et al. And David Mimno, that basically goes into great details of all the different aspects of what to use for or what the impact is of different pre-processing decisions on the final model. I think it's a very good paper. It's very thorough, very, very informative. I saw somebody also posted something on like qualitative analysis. I also posted a link to a prior iteration of the NLP class I'm teaching at Bocconi with Jupyter notebooks, Python notebooks for the different topics. So this includes a lot more than topic models. That's just one lesson, basically. There's also a link to the lecture notes, which is sort of a write-up of a lot of the material. So if you want to read it, this is, I think it's about 200 pages with images and everything, and also some code snippets. So, that's like a resource that you can also use. Depends on what your learning style is, right? Some people like to read things, some people like to see images, some people like equations more. It has a little bit of everything. And then there's also the code. So there was a very interesting question, the debate on whether LDA can be performed on TF-IDF. I only got to skim it now during the break. It seems there is an argument in the original paper by Bly to not use TF-IDF. TF-IDF was something that was used with LSA, which is a latent semantic analysis, which is an older technique to find latent topics in the data. And that LDA doesn't need that because it overcomes it. Somebody then argued that it doesn't make sense to weigh frequencies by fractions. So TF-IDF typically is like it's not an integer number, it's a real valued number, and that it wouldn't make sense. Now, I could see that this, I believe the original implementation of LDA was implemented using Gibbs sampling, a sampling technique, which means that it does rely more on like actual counts, integer counts. Inherently, it does make more sense. The implementation in GenSim that we're also going to be seeing in the notebook, and that seems to become more prevalent, is based on an algorithm called expectation maximization, where, without going too deep into it, you're collecting fractional counts in each iteration, and then you're normalizing that at the end of the iteration or at the end of a batch to become a probability distribution. But during an iteration, it's not constrained by being integers because it's normalized at the end to form a probability distribution that sums up to 1. It doesn't matter what it is in between. That is fundamentally what EM actually builds on. So there you can actually have fractional counts. So you can say, oh, I have seen this word 1.67 times rather than 1 times or 2 times. And then because it's turned into a probability later on, this sort of like logical inconsistency doesn't make a difference. So my counter argument would be that I could see and I can understand why conceptually TF-IDF wouldn't make sense in a Gibbs sampling based implementation of LDA. I believe for an EM, expectation maximization training based implementation of LDA, it probably wouldn't make as much of a difference because you could use those as fractional counts or weights on the individual tokens, which is also something that's done in other implementations of EM. I've worked a lot with EM during my PhD, and that was a very common thing to do. So, I've only looked at it briefly, but that would be my quick and dirty explanation. So I think it is okay to use TF-IDF, and empirically it seems to give good results. This is a big difference between statisticians and machine learning practitioners. sometimes like machine learning practitioners will say, then multiply this by 6, and then statistician says like, why? There's no, guarantee theory or like any proof that this should work. And machine learning practitioners will just shrug and say, yeah, but empirically it gives good results, so just do it. Sometimes the proof is in the pudding, and yes, conceptually seeing a word 1.5 times doesn't make sense, but the algorithm doesn't care about it because it normalizes it into probabilities in the end. I don't think it makes too much of a difference, and it can sort of guide it, or give more weight and more influence to interesting words rather than, sort of like non-interesting frequent words. Okay, hope everybody has gathered back. So let's jump back in. Okay. There. All right. There we go. Okay. Actually, that was a pretty good segue. So thanks for posting this, Jay. Because we're going to talk a little bit about the training, not too much, but I want to have you understand a little bit about what's going on under the hood. So we said, okay, we take LDA or some other topic model, we give it a corpus of documents. We say, I think there are n topics in there, let's say 5, and I think they're going to be, there's going to be very few topics per document, and I think each word is going to be very indicative of one topic. So the words are not going to be shared between topics. So those are my alpha and beta parameter and the number of topics. And then I give it the corpus, and then LDA or whatever other topic model I use runs and does its thing and comes back and says, okay, here's your theta, the distribution over topics for each of the documents in the corpus. And here's the Z, which is the distribution over words for each topic. Okay, so that's where we are. So now how do we know? So we said things can vary a little bit depending on where we start, depending on all the parameters we choose. So how do we know we're getting anywhere? How do we know what's happening, right? So this is how do we evaluate LDA and how well it's doing. So there's 2 types. One is model inherent. Because this is a probabilistic model underneath, we can, during the training, look at what is the data likelihood? How likely is it that the data that we see, that we observe, that's in our corpus, would have been generated, if we accept this weird generation process, by this particular model at this time point? A property of the expectation maximization algorithm that is used in the Jensen implementation is that with every iteration, the data likelihood increases. Like it should get better. So the model should find a better, more consistent explanation of what it sees and find a better way of explaining what we have asked it to explain. Now, that is good. We can use all kinds of metrics that are based off of that. So the model might find a coherent explanation that increases the data likelihood, but it's completely illogical to a human observer, right? And we wouldn't catch that until the end. So there are things like entropy that we can, or perplexity, and entropy, perplexity is based on entropy, that we can measure and we can use, and we can say, oh, if it has a better perplexity, then it's a better model. And that's one way of selecting a model. So if we run several models, everything else being equal, we could pick the one that has the best perplexity. So that would be one way of choosing a model. The other one, and this is maybe more relevant, is, well, what we care about ultimately is a model that gives us decent topics, right? That we can interpret, that mean something, that give us some insight, right? That allow a qualitative analysis of the data that makes sense to us. So, this is a good topic, right? We would look at this topic and probably most people would say, I think this is the topic we call fruit. So, and, we can do a test and we can basically replace one of these words with a random other word. And hopefully, you know, if we did this, it would be obvious to every sensible observer that, you know, the odd man out, the non-fitting word is this word foot, right? Everything else is a fruit. This one is a body part, so that doesn't fit in there. And so basically, we can use this as a way to evaluate models by asking a panel of people to say, okay, which one of those is wrong, right? And if people have an easy time to spot the intruder word that we put in there, then that means that the topics our model came up with were pretty good to start with, right? Because by changing any one of the words, we made it very obvious which word we changed, right? If, however, the model found kind of random lists of words that constitute a topic, and we change one of those words, and the people that we ask cannot spot that word, that means the purity, the coherence of those topics wasn't very good to start with, right? This is called the word intrusion test. Now, one of the most important parameters that we need to check is K, the number of topics that we have, right? Because obviously, you know, whether I ask for 5 topics or 500 topics, that makes a difference, right? And again, this is something that I, as a researcher, have an intuition about in the beginning, right? I might not know the exact number, but I might have a sense of the range. And it might also be determined by the granularity of what I'm interested in, right? Oftentimes, several solutions are possible with 5 topics and with 20 topics and with 50 topics, but they'll be more or less fine-grained, and it depends on what I'm interested in. What I can do is I can run models repeatedly, vary the number of topics that I want, and observe an outcome value of the coherence of the model. How good is the model? How coherent are its topics? And then, you know, I plot them on a graph like this, and I basically then, you know, choose the best score, you know, that I find. Either the first best score, so here it would be 8. If we let it run longer, you know, maybe we see that around 16, 17, there's another peak, and beyond 20, there's an even higher peak. But it dips in between. So, you know, maybe those other ones are also good solutions, but we want to, you know, we're happy with just having 8. So this is a good way of choosing the number of parameters. Now, the question here is, of course, what's on the y-axis, right? What is this measure that we're using? So, and that could be either one of those inherent measures like perplexity, that just is the probability that the model assigns to the data, or it can be a coherence score. Now, if we want to test 50 different topic values, we cannot go back to a panel of people and ask them every time which of these is the intrusion word, and like, you know, and then sort of calculate how many of them got it right and how many of them got it wrong, and what does that mean for the model, and then plot that and then choose it. I mean, we could do that, but that would take so much time that it kind of defeats the purpose of having an automated tool a little bit, right? Yes, we want a human in the loop, but we don't want to set up a full panel every time just for choosing a parameter. So as an alternative to that, people, you know, glommed onto that pretty early on. And computer scientists love metrics that correlate with human intuition. So they came up with these different coherence scores. Here are 2. There are more of them. One is called UMass and the other one is called CV. And they correlate strongly with the assessment of panels of human judges on the coherence, on the quality of topics. They do this by computing a couple of things. So they basically say, okay, for each topic, I'm going to look at all the words in that topic, and I'm going to then compute how likely are these words to occur together in the data that we have seen, and I'm going to take the logarithm of that, and that is basically going to be my my coherence score, right? Alternatively, I can look at the pointwise mutual information. So like how often do these words belong together in a text, and the cosine similarity between the words in a vector space. We haven't talked about this today. We've talked about this yesterday. We can represent words as points in a large dimensional space where the position of a word with respect to all the other words is determined by its semantic similarity to those other words. And so if all the words in a topic happen to be close together in this vector space, then great, right? That means that this is a very, semantically coherent word. So this CV score is sort of like a joint score of these two. They have different scales, and they're slightly different to read, but we can use those as an approximation of what a human panel of judges would say about the quality of topics, and use that to choose, for example, the number of topics that we have. Alternatively, we can do word and topic intrusion tests, right? So this is what my former student handed, where you take a topic from the model, right? And you just add a word in there. So here, the topic was defined by loud, music, sound, quality, and speaker, and she added the word time, and then checked whether people would, recognize that time shouldn't be in this list, right? And then the percentage of people that correctly identified this, that is essentially the quality of the model. You can also do topic intrusion. So you get a sentence, for example, I get my morning facts and news all in one easy to use system. That is your sentence. And then, she said, okay, here are 4 topics that the model identified to be present in this sentence. Easy use, setup, simple install, control, command, system, integration, smart, music, weather, news, alarm, timer, or price, buy, sale, deal, item. Which of those, did I make up? And then if people select the last one, again, that proportion would be sort of the topic, the overall topic distribution quality. This is a topic intrusion test. So those are ways in which we can evaluate our model and sort of automatically choose what we get, right? So we said there's all these parameters that we can set. There's the number of topics, there's the alpha, there's the beta, and we can use those. We can evaluate the best values for that by repeatedly running the model and then choosing a coherence score or the perplexity or some other measure or a combination of those to select which parameter settings we want. However, we might also be able to add constraints to the model, right? So oftentimes when we work with data, we don't need to discover everything from scratch, right? There's some element of discovery. There are some things, for example, like in the parliament discussions, we weren't aware that there is a frequent topic of childcare, right? And we can discover this. But we're pretty sure that there's going to be something about unemployment and about the economy and about maybe climate change, right? So we can do some things here to basically nudge the model in that direction and say, look, you do your thing, you please find the theta and the z that best fits the data. But I happen to know that, if whenever you see this word, like it should have a high probability for this particular topic. So we can sort of add a constant to some of the words for one of the topics and say, look, this is probably going to be the climate change topic, right? So whenever you see the word, emission, right, that should have like already a higher probability for this topic number 5, which, I think will be the topic for climate change. So this is adding constraints to the training. Another way to do this is to use an author topic model. So here we have covariates. We know something about the documents that we're working on. For example, we might know the country that it comes from, or we might know the author who has written it. So that's also why it's called sometimes the author topic model. There's a scientific paper about it that was called the structured topic model by Roberts et al. And I can post a link to that later. And so this way we can say, look, I know that different, that this covariate, that where the document comes from has an effect on the topics, right? Not everybody uses the same topics to the same degree. So please take that into account. The way this works is that we change essentially the structure, the architecture of our model. Essentially, what we're doing is we're taking this model, which we've seen before. You don't have to remember everything about this. And we're going to change this slightly. Was there a question?
No question, just a comment on the structural topic model.
Ah, okay. So essentially what we're doing is we're going to move this this element out of this, and we're going to add another random variable in here, A, which is the author identity. You can see that it's gray, it's shaded. It means we know this, right? This is not something that we asked the model to find, but we actually say that this author identity influences a random variable called X, which is specific to each document, and this actually influences the distribution over topics. So we basically are, introducing like another influence factor here, and we're asking the model to not only find, the valuations for theta and for z, but also for x, right? And we say that this is influenced by the identity of the covariate. And essentially then again we let our model run with all of these constraints, and we say, can you please find the most likely explanation of the data under these settings, under these constraints. Okay, so where does that leave us? All right, we have a bunch of data. We want to learn more about this data. We think there's some, underlying topics underneath. Maybe we're interested in the general distribution of them. Maybe we're interested in the distribution over those topics for each of the documents, or maybe just like what is the most prevalent topic for each of the documents. We need to pre-process this. We need to, get rid of all the noise words. So we make our topics as clean, as coherent, as consistent as possible. Then we set up our model and run it with all of the constraints that we set, which is the number of topics, the alpha and beta parameters, maybe the author or like the covariate identities if we run an author topic model or structural topic model. And then, we have to do an analysis and choose the right parameter settings. And then once we're satisfied with that, we probably still want to run the model 3-4 times and look at what is stable, what is changing across different runs, and then sort of focus on the stable topics to give us an insight into what's going on in the data. What we get as topics, right? A topic is going to be described by the 5 most likely words under that topic. And then what we have to do is to find a good label for that. We don't have to, but typically that's what we want to do in order to refer back to it. And again, this requires some domain expertise, some understanding of what this topic mean, and that oftentimes can, be more tricky than we think. It requires some knowledge of the domain we're working in. Was there a question?
Yes, we have a question by Edward asking if the STM is the same as using LDA for calculating the theta and then aggregating them by authors?
It's a very good question. It's similar, but it's not the same. And actually, we're going to see this in the notebook. If I understand your question correctly, you can do this. So you can run LDA and then aggregate by the covariate. What that will do, this is an aggregate, this is an average over distributions. What that means is that you will have sort of like a baseline of like every topic is everywhere a little bit, and then there will be some peaks, but they will be less pronounced. When you instead run the STM, the structural topic model, you get a sparser distribution because you already incorporate this distinction into the training process. You're not averaging over something, you're already like making a distinction from the start. You say, if this comes from the US, I assume there's a different distribution over topics, like people there talk about different things than they do in Italy, right? And so you're making this distinction earlier, so you oftentimes get more distinct topic distributions. They're sparser and they're going to be more distinct than if you aggregate by averaging.
Okay, we have another one by Jay. He asks if topic modeling can be done on word embeddings.
Yes, absolutely. So there has been, so word embeddings is this, we're going to take, just for people who are unfamiliar with the term, you take words and you project them into a large space, and the position in the space is essentially determined by the similarity to all the other words in that space, meaning all words that are close together mean similar things, occur in similar contexts. Words that are further apart in this space are words that never occur together, that mean different things. This has been introduced. There were versions of that, predecessors of that has been around since the 90s. There was an algorithm introduced in 2013 by Mikolov et al. That sort of made this contextual similarity part of the learning process. And the results of those word embeddings were pretty impressive. So if those were used as input to models, they generally produced much, much better performance, while also being smaller vectors. So we said, like in our example, every word in our vocabulary is like one dimension in our vector. So if we have a very large vocabulary of 5,000 words, we have 5,000 dimensional vectors. With these word embeddings, we can say, I want this whole explanation in 50 dimensions, right? So naturally, people started asking, oh, well, I mean, it seems to work for classification. Does it also work for topic modeling? And the answer is yes. There's a lot of work that has been done on this. I'm going to show a slide in a second. So there's fantastic work that has come out, I think, also from David Bly, one of the original authors of LDA, David Mimno, and also in my lab, we have just published a paper or a library, well, 2 papers about a library that you can download, a Python library that uses some of these word embedding models to do topic models. And I'm going to talk about it in one of the next slides briefly, but what you see is it has certain advantages. It's more flexible than using words. It's more coherent, and it can be used across languages, and has a couple of other advantages. But before we get there, I wanted to say, we talked about this throughout, topic models are not classifiers. They don't, they're not deterministic. They don't take away all the work for you. They can help you make sense of large amounts of text, but they need you to be involved in the process. So they're like a very busy coworker that can plow through a lot of text in a short amount of time, but they need your supervision. There's variation in there, so you need to always check. You cannot just rely on probability. Models will always find the most probable explanation. That doesn't mean that's something we as humans recognize as a good solution. And you need some domain expertise, right? So think about the Bluebird decoder encoder transformer topic. If you don't know machine translation and neural networks, that topic that looks like garbage to you. If you do, then it is actually a sensible, coherent topic. So, always be involved in the different steps and the output of the models. There was a question, I think.
Just thanks.
Oh, okay, good. Yes, and please do never use topics as input to regression. Just because of the variability, it just makes it basically impossible to reproduce. So here are some of the take-home points. LDA, the granddaddy of topic modeling. It's a probabilistic model. It assumes that documents have been generated in this weird way of like drawing distributions and then drawing words from those distributions, and we can reverse engineer this process to learn the underlying parameters. They're stochastic models. They are hugely influenced by what you do to the data that you put in. The old machine learning saying, crap in, crap out, holds also here. So do take care of what you feed your models. And I can highly recommend this paper that I posted. And you need to be involved. This does not absolve you from doing some work. It can automate a bunch of important steps, but you do need to be involved. There are variations of topic models that allow you to imbue the model with the prior knowledge you have. You don't have to always let the model discover everything from scratch. There are different ways in which you can nudge the model in the right directions. We've talked about the covariates in the structural topic model or author topic model. There's also guided or semi-supervised topic models where you can use labeling of some instances to guide the model and constrain it and make some things more likely than others. And there are other ways in which we can guide it. So there's a huge variety of topic model architectures and versions that are out there. One that I wanted to briefly introduce here because I'm familiar with it and because it comes from my lab, Milano Proc, is the contextualized topic models, or CTMs. This is based on neural networks on word embeddings. What we find is that it has a couple of advantages. The coherence of the topics tends to be better. The other nice thing is because of the way these word embeddings are trained, it's no longer language dependent. So you can, for example, train on one language and then use it in the future on other languages. Oftentimes you have a lot of data in English because it's a very prevalent language on the web, but you have a small amount of data in Chinese, in Italian, and other languages, and you kind of want to work with that. With this, you can actually, train it on the language you have a lot of, and then also use it on the others, and sort of compare across languages. And there's now also the option to add labels to documents similar to author topics, which can guide the learning process and sort of make it a little bit more, guided and a little bit more understandable. As a plus, it also has a cute cat as a logo. Here are some examples of what we found. So this is Wikipedia articles. This has been trained on English to find the topics, right? So, and then if you run it on the Wikipedia articles in those other languages, for example, in Italian, Portuguese, French, or German, you can see that, even though these are different inputs, different languages, it does correctly find the correct topic or the same topic also in those other languages, even though it hasn't seen them during training. So, makes for a nice way to work with different languages. There are questions?
So first, a question about the package. Did you ask if it's a kind of transfer learning?
Yeah, this is a form of transfer learning. Yeah. So using word embeddings or cross-lingual word embeddings is a way of transfer learning. This even does what is called zero-shot learning. Basically, you train only on English. You never see anything in Italian, and then you have one shot or 0 shots, you just immediately go to the Italian data and see what comes out of that. And this is a way of transferring between different languages. Yeah, absolutely.
Then the next question is, would you say there are models that are usable for regression? I know that in communication science, people are using, for example, factor analysis to detect frames after pre-selecting issues, using supervised models, then using the prevalence of a topic as the independent variable to, for example, explain public opinion shifts. Would you recommend using something else, for example, supervised modeling to measure prevalence of frames, topics to be used in a regression?
Yeah, so as input to a regression, I didn't realize this would be such a sticky topic, but I understand the concern. Factor analysis is different, right? Because factor analysis, depending on what kind of dimensionality reduction or factor analysis model you use, for example, if you use SVD, that is deterministic, right? So that would be fully reproducible. If you first run SVD on something, you get the latent factors. Let's say you chose 17 latent factors, right? And then you use that as input to a regression model. That is completely, the pipeline is fully reproducible. There's no stochasticity involved. There might be others if you use non-negative matrix factorization, which is non-deterministic, right? So that wouldn't work. But there are factor analysis algorithms that can be applied to deterministically produce the input, which can then be used to regression models further down the line. I think it would also be a different story if you used several runs of a topic model and you sort of averaged over the prevalence of a particular topic or the average probability of a word or a topic over, let's say, 10 runs, right? And you use that, and you use or you use the change, the relative change in that as an input. If you use averages over a large number of runs, the law of large numbers means we should, be able to reproduce that, because it would always sort of converge to the same average score. So that, I think, would be a slightly different story. But you cannot use a single run and then use the topic proportions or probabilities as input to a regression, because that would not be fully reproducible. And like basically the results, the conclusions you would draw from that might or might not be right? And like you might be unlucky and just get a topic distribution that completely contradicts your hypothesis, or you might be lucky and get one that perfectly confirms it. And yeah, so that's a little bit trickier. Something you can do is use word embeddings and then cluster those, for example, with agglomerative clustering, which is deterministic. It's basically deterministic under the right conditions. You would get, and you could use that to group, to find latent topics and group your data, and you could use that as input for further models.
Then Johannes asks if there is any disadvantage of using LDA to further analysis with regression, or
right. I mean, you cannot use it as input, right? So you can use LDA first, and under the conditions that I've shown, with the caveats, by observing what are stable topics, what is going on, it can inform your understanding of the data, of the corpus, and of what to pay attention to. So for the example, like what we did in this COVID data project, that using topic models, we were able to identify recurring themes, which we then included in our labeling or coding annotation instructions to annotators to like look for in the data and make that a category that we want to analyze. And that we could then, once we had that labeled by trained human annotators, we could use those labels to train a classifier on it. Yeah. So they're using the topic model sort of was a first step to understand the data and understand what the taxonomy of categories are that we might want to code for in the data.
Sorry, Johannes, I misunderstood your question. Actually, Johannes wanted to know if there are disadvantages in the model on the last slide.
Oh, this model, the contextualized topic model?
Yeah, from the last one that was mentioned in the slides is, yeah.
Yeah. So again, this is learns. It's a neural network architecture, right? And so again, neural networks are initialized randomly, and it learns part of the distributions from observing the data. I believe sort of the variation is less than what you see in like the probabilistic models, but still there is some variation. So again, you could not use it as input to other models, but what we've observed is that along a variety of coherence measures, it does perform a lot better than LDA and a lot of other topic model variants that we've compared it to. So it can, you can have a lot more confidence in the results that it gets, and it has these advantages of like being applicable across languages, for example. But still, it it has an element of stochasticity.
There is one last question. If you know about any implementation of topic modeling using word embeddings in Python or R?
Yes, this one. So there is. So this one does use a model called BERT, which essentially produces document embeddings and word embeddings as part of that. This builds on prod LDA and like other sets of neural language models that can, so there's a class of models that take as input, a class of topic models that take as input word embeddings. If you go to this website and you look at the papers that are listed there, there's a comparison with all the relevant literature of the topics. What I can do is I can post the relevant papers for this model here. And what was the other model? Oh yeah, the Roberts model on the structural topic models. I can post those in the break, or yeah, we can take a 5-minute break after this, and I can just post those before we go to the notebook.
There are no more questions.
Okay. Oh wait, was there? Oh, right. Oh, I skipped this because I thought it might be a little bit too complicated. I just want to show you this real quick because I think we have covered it, so it won't be too complicated and like it's not going to derail the discourse. Here, like I wanted to talk about this underlying training algorithm, EM expectation maximization. Essentially, you're trying to find these two distributions, theta and z. That's what you ask LDA to do, right? And typically, when we have supervised learning or like we have data, we can just count and divide to get those probabilities. So you take counts and you divide by a normalization factor. But here we cannot, we don't have anything to divide by, right? Because we cannot observe these things. So what we do is we use expectation maximization. We initialize theta and z randomly. We hypothesize some setup of those. And then we basically, we go through and say, okay, assuming that theta and z are correct in this current form, what would be the explanation in the data? How often would I see each topic? How much would each word be correlated with each topic given the data? And then I would keep track of those counts, and I can multiply those counts with the TF-IDF values to up or down weigh them. And then at the end of each iteration, I would normalize those counts and update the theta and z parameters respectively and say, okay, now that I've seen all the data, I think I need to make updates to my theta and z that I initialized randomly. And then, I do another pass over the data with these updated theta and z. And again, I, see how much that explains the data and I make updates to it. And I do this until it converges. So until the changes become smaller and smaller and smaller below a certain limit. And so essentially what we're doing is we're asking the model essentially we're dropping the model off at some point in this alpine landscape, and it doesn't know where it is. It only knows it has to climb up and find the highest peak it can reach. So that's the model's goal. And so that's what it does. However, if we dropped it off at some other point, the model might do exactly what we told it, find the highest peak it can reach, but that might not be the highest overall peak. So a lot of these models or initializations will not end up with the best possible model. And so, by adding constraints, by saying, okay, I know we don't have to search this area, we don't have to go somewhere where it doesn't make sense, we can sort of guide that process a little bit. Okay. Oh, I see there's a question about neural networks. It depends. So a lot of like modern neural networks do not require pre-processing. They are trained to sort of take text as is. They will sort of like take word snippets and work with that. And then they have enough parameters to deal with all of it. It can help though to sort of like standardize your input a little bit to, again, guide the training process for the model a little bit, make it easier for the model to find the correct solutions. All right. Any other questions? Okay, so let's take 5 minutes. I will post the links to the relevant papers that I just mentioned. And then after those 5 minutes, we'll go to the Colab notebook, and I'll show you a couple of things, how to implement this in practice, and point out a couple of things we want to take care of and we want to see, and sort of how some of the stuff we have talked about in theory pans out in practice. All right, so see you in 5 minutes. Okay. I very much enjoy this sort of smooth jazz intermission music that's going on whenever there's a break. Very relaxing. Okay. So enough of all the theory. Let's get our hands dirty with some practice. So let me share the notebook that I've prepared and that you all should have a link to, I believe. So this is, oh, by the way, so yeah, so here's a link to the class. This is an earlier iteration of the class that, you know, I haven't updated much since like 2 years ago because we moved to a different system. All of this is still valid. Some of the code might, you know, need some updating, but should be functioning. You have like an overview of the class and the lecture notes here. So if you want to dive deeper into this, you know, this is another resource for you. Okay, so topic models in Python. We're going to use a little bit of text it's a Kaggle data set on wine reviews, I think from the website Wine Spectator. You know, to make it workable for our purposes here, I've reduced it to the top 50,000 descriptions of wines from France, Germany, Italy, Spain, and the US. I've also pre-processed the data. I've used this pre-processing function here. It's commented out, so you know you don't have to rerun it. It's already in the data, but if you want to reproduce it, basically I'm using the Spacey library, and I throw out everything in the data that's not a noun, a verb, an adjective, an adverb, a X, which is sort of like foreign words and expressions, and a proper name. And then of those words, I lemmatize them, and that's the text. Because this is a Colab notebook, you have to pull this from my website. It's an Excel file, but could also be CSV file or whatever. Then we can read it in. Here's what it looks like. So this is the original description, right? And then here at the end, we have the clean description. You can see how a lot of these things, you know, get reduced quite a lot. So aged in 100% new French oak, this dark and muscular wine, blah, 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 becomes aged new French oak, dark muscular wine, have lush. So it's, you know, a much more simplified version of what's going on. We have the country here, which we're going to use later as the covariate. And then there's all kinds of other information, which for our case now is not super relevant, but you could also use these other things as covariates if you wanted to. Was there a question?
Yes. What's an average length of a description?
What's the average length of description?
Yeah.
That's an interesting question. So let's say.
He meant wine description.
Yeah. Oh, right. Sorry. It's currently running some other. It's fitting the model down here. So it's, yeah. We have to wait until it's finished running the models. I'll come back, but it's, I'm going to say around 50 words, maybe. It's like a section. It's like a paragraph, typically. Yeah. We'll get back to that. This is going to execute once it's. I've already started the notebook because some of the training of the models takes a few minutes, and you know I didn't want to idle and have you wait for it. So we got to wait until the others are finished, and then we can do this. So here, basically, we're going to use this GenSim library, which has nice implementations of LDA. It has a parallelizable version of LDA, which is pretty neat. It also has a TF-IDF converter, and it has these coherence models that allow us to check how good is the model. We're going to see that used in a second. It has a convenience function of dictionary. So basically, it will go through the data. It will figure out how many words are unique words are in my data, and then it will ignore all the words that have less than or more than a certain count or percentage of the data. And we have this phrases thing, which basically produces collocation, so joins words together that frequently occur based on their pointwise mutual information. We're going to have a couple of other functions that we need to check things, so like the timing and to find out how many processes we have available. So this is what the data looks like initially. It's a list of strings. So we're basically taking this column of our notebook, we're splitting it on white space, and we're forcing it to be a list. So it's a list of strings. This is what the first one looks like. On that, we will first find all the phrases, the collocations that are in there. So like New York, New York. And then based on that, we're going to build the dictionary of individual words. Note that we could run this part several times, and that way we would merge not only bigrams, but also trigrams of collocations. So something like World Health Organization. So if you repeat this step, then you'd get larger collocations. Then you create the dictionary. So after we merge the collocations, we say what are the unique words. Collocations obviously are unique words then. And then we basically filter this. We don't want any words that occur fewer than 50 times or more than 30% of the data. And you see here, like already it has merged some of these first words, age new and French oak, wine half. This is a little bit of a funny collocation. Cut tobacco, cassis fruit, black olive. So, most of these herbal element, most of these are pretty sensible. Questions?
No, he's just explaining that he asked about the length of, because topic modeling is usually fit for a bit longer and not short texts. So if it would work for wine descriptions.
Yeah, it does. It does. You can also use it for short text. So I've also used it for tweets, and it does work for that as well. But you have to, like make certain changes depending on the data type or the text type.
Okay.
So then, once we have our collocations and everything, we will go and we will replace each word with a unique ID and with the count of that word in that sentence. So here you see age new gets translated to 0, French oak gets translated to 1, dark gets translated to 2, and so on and so forth. And you can see each of these terms occurs once. So the second part of these tuples is always 1. That's the count of this particular token in this particular document. And then we run this TF-IDF model, we train it on the corpus, and then we transform the corpus. And so now you can see that instead of 1 for everything, we have very different TF-IDF weights here for the different expressions, right? So some of them get down-weighted. I mean, all of them are less than 1 now, but some of them are larger and some of them are smaller. So now we can set up a model. We will take a subset of the data, only 15,000 instances, just for speed reasons. You could use it on the entire data. We're going to range from 5 to 15. We're going to fit a parallelized LDA model on this subset of the data. We use the dictionary. We have chosen a number of topics, which is here ranging from 5 to 15. And here you can see I'm using a random state, 42, to make it more reproducible. We then pass that information into one of these coherence models to basically evaluate how good is it, and that will return a score to us, right? And then we will print that out and also store that, this triple of information. And you can see here, you know, varying the amount of information, we get sort of different outputs. Let's actually plot this. Might be a little bit easier to see, right? You can see here, this is the UMass score, and this is the CV score. It seems 14 is a pretty good. So here the UMass score, it seems like lower is better generally. For the CV score, higher is better. But like I said, you know, maybe we want to start with 7. There's a peak here, and then there's this valley in between. So maybe 7 is a fairly good starting point. So we set our topics to 7. We then make 10 passes over the data. We make about 200 updates. So that these like details of the EM algorithm. And then we're gonna fit our model. We have to choose the number of topics, which we've selected based on our eyeballing it. We're taking the corpus, the dictionary. We are parallelizing this to 10 cores, or, you know, however many the computer has. We do 10 passes over the data in chunks. So the chunk basically means go through the chunk and then update the EM algorithm. Alpha is set to 0.5 here. And again, we have a random state at 42. And so, yeah.
There is a question of Johannes. What about the collocations that don't make sense to us? Do we just ignore them?
So for now, we can ignore them. If you want to, you can modify the dictionary, right? You can add this as stop words and remove them. If you go through and you see that they end up and polluting your topics, then you could go back and take them out. Yeah. If they don't end up in the topic descriptions, then you can just ignore them.
Okay.
So here, yeah, by the way, we got this information. Right. So our topic has around 2,600 unique tokens, right? So these are the different words in our vocabulary. So we fit our model. Here it took 284 seconds. So what is that? Almost 5 minutes. And which is not too bad on 50,000 documents, right? And then what we can do is essentially we can apply the model to the entire corpus. And that will basically turn each document into a distribution over topics, right? So it will basically just say, okay, document 1, our distribution over the 7 topics is 23% is topic 4, 15% is topic 5, 30% is topic 6, and then there's like a smattering of these other topics. What are the topics? Well, here we can use this print topics, and it will tell us for each of the descriptor words, I think it's the top 10 descriptor words, the prevalence of this word in the topic. This is a little bit hard to read, so we're using some regular expressions to cut it up and make it a little bit more readable. And so we get this here, right? So here are 7 topics. The first one is about spice and aroma, I guess mouth feeling, year, rich, balance. So it's, you know, maybe we want to get rid of that and like move that out and make it a stop word. We have this here about simple, clean, citrus crisp. So this seems like a description of a nice white wine, light white wine or something. Drink now, oak, good, be very, dry. Okay, so this, these are all kind of flavor profiles of wines that we get here: black cherry, tannin, plum, full bodied. You can sort of imagine a wine with those characteristics. Here, fruit character, acidity, tannin. So this is a slightly different one. And, all of these others, right? So these are kind of descriptors of, I guess, different wine profiles, wine flavors. Was there a question about it?
No question.
Oh, okay. And so somebody asked this question, so we can aggregate this by the covariate, right? Yes, we can, right? So this is one idea. We'll use the country. So this is a sample of the data, right? So we have various columns of information. We have the country, we have the number of points we got, we have the province it's from, the region, sub-region, the wine variety, and even the winery that produces it. We could aggregate by any of them, obviously, if we wanted to. Here, let's choose country and see what we get. So here, I made this a variable so it can be changed if we wanted to. We're basically gonna get all of this information. We're gonna aggregate it and turn it into a data frame, right, where we have the scores and the columns are the descriptors. So we have 7 columns. And then for each document, we get the distribution over the documents. So yeah, that is kind of the output, not super informative. So let's aggregate this. Pandas data frame allows us to group by the category, right? In this case, the country, and then we can just plot it. And this is what we get, right? And so you can see here fairly nicely that the different countries, so you can see 2 things. One is what I mentioned before, there's a substrate of every topic for every country, right? So you have like at least 10% of every topic in every country. But then there are differences for the country. So for France, we have topic 2 and topic 6, right? So I forget what topic 2 was because it's is not, okay, year, rich, balance, fine, right? And topic 6, fruit character, acidity, tannin. Okay, so these characterize French wines. German wines are characterized by this green topic, which was the sort of white wine topic, which makes sense. Germany produces largely white wine. Italy, spice and aroma. Some of these, some heavier red wines and some white wines. Italy has also white wines. For Spain, there's a lot on this fruit and character and what was it? Feel, acidity, tannin. Yep. It's kind of Riojas. And then we have the US. There's a lot of this drink now, oak, heavy, full-bodied, right? This describes like American red wines typically. So yeah, it kind of, neatly gives us the different wine flavors that come out of it, and we can aggregate that by country. Question?
Yeah, there is a question from YouTube. Do all topics always have to make sense, or are residual topics allowed as well?
Very good question. Very good question. No, so especially if you have larger number of topics, there will be sort of like the leftover or garbage topics that just, kind of the model has to do something with it, right? So it's just going to put everything in there. And there might be, if you choose 200 topics, there will be a lot of them that look very, very similar, just different orderings of kind of like random words. And out of the 200, there might be like 20 that are super interesting to you, right? So this is, again, something that requires some analysis and like a human in the loop. But yeah, not all topics need to be sensible. So, okay, so this is the aggregation. So this is what the model gives us, right? So we can get a distribution by document. So we can, if we're interested in knowing what each document is about, right? So this, document The third document with the ID 2 is to 20% about topic 2, 3, and 4, right? So that describes that particular wine. But then we can also aggregate that by larger categories, and we can sort of discover that there are predominant flavor profiles or flavor notes for wines from different countries. So, however, as you can see, because we're averaging over 50,000 instances, there's a little bit of everything everywhere. So maybe we want to thin this out a little bit. So what we can do is, I wanted to check one thing. Yeah, okay. So we're getting this topic model, author topic model. We're doing very, very similar things. One thing we have to do first is we have to create a mapping from each covariate, so here country, to the IDs of the documents that are associated with this. So this is what we're doing here. We're mapping this to the different categories, and basically creating this dictionary that we get. So for author to doc, for a particular covariate, which are the countries here, we get a list of all the document IDs that are associated to Italy, right? And then we do exactly the same thing as before. We have to subselect our author mapping, our ID mapping to covariates a little bit here, but then again, we run the same thing, right? Just now we use an author topic model. This is the big change to before. And we have to give it this author to doc keyword. So those are the differences. We change this and we change this. Everything else stays the same. Here we run it for fewer instances. These are the plots we get. Actually looks like 5 is already the best. Again, like UMass lower is better, it seems, and CV higher is better. So let's go with the 5 here. So we just train the model again. Same thing, very, very similar. And then we can, the output of this is slightly different. So we extract the topics in a slightly different way from before, but here we see the topics that come out, and we see it's kind of similar. It seems like topic 4 and 5 are largely similar, except for different orderings, and that, topic 4 also has acidity in there instead of the other one. But again, these seem to be different profiles of different wines. What we can do now is we can basically make a distribution over all of the topics for each of the covariates. Some of them are not defined. So if we've never seen a topic for Italy, for example, it will not be defined. So we have to sort of initialize it to 0 and then override it with the value we've seen. So the output looks like this. So for each covariate, we have a mapping for each topic, right? And then again, we can make a print of this, and you can see again, or you can see two things now. One is the residual is much lower. So for example, here, topic number 2 does not exist for France. Topic number 4 does not exist for Spain, right? And everybody has this one predominant topic, which is much, much more pronounced. The probability is much higher than before. And you can still see that, this is sort of correlating to some of the same things that we have found before. But again, it requires some interpretation and some looking at the topics. So for space reasons, I only show the first 2 words here. Typically, you say it's a good idea to show the top 5 words of a topic. Fewer might be confusing. As you can see here, just 2 words, is not enough to really get a good sense of what this topic is about. More just can become a little bit noisy and a little bit bloated. So 5 tends to be like the best possible option. Yeah, so those are the two different ways we can use this. There was a question about the length should be done computing. Oh, okay. Sorry. After cleaning, the average length is about 26 words. Yeah. Questions?
There is a question from Johannes. He's getting 10 topics instead of just 7. Is it already because of the random factor? And then there is a similar question from the YouTube. Someone is also getting different results even after setting random state argument. So
yeah. So I guess this is the variation that you get across. So the 10 might be, I was playing around with this earlier, and I think I set this first set of topics to 7. So if you go to this thing, so you don't always get the exact same results, right? So the random state can help control some of the variation, but this might again be this difference that if you run it on different processors, different machines, you might get slightly different results. So there's still like a fair number of variation in there, right? And so you will always have to like rerun this and then pick the best topic for you in this thing. Actually, here it seems 14 might be an even better number of topics based on the coherence scores. So yeah, there is some inherent variation even across the different runs with the same random seed. Actually, let's see what happens if we run this. It's going to take a while now because it takes about 5 minutes to run. Other questions?
No other questions. Johannes only said that he had forgotten to change number of topics to 7.1, and then probably that's why.
So Johannes, you might want to change it to whatever is the best score in your run with these coherence scores, right? So the lowest UMass or the highest CV score, or the first best CV score.
There is another question. I am working on topic models like LSA, LDA. I am a bit confused which evaluation metric to use for comparison. So my question would be, what are the various evaluation measures for topics models?
There is, so if you look at the paper that I posted in the chat, there are a couple of coherence scores or a couple of evaluation metrics. Actually, maybe we can look at that together. That right here. Now let's share the screen again. Okay. So this is this paper that we recently published. This is the architecture of the model. Let me actually zoom in a little bit here. So it takes these contextualized embeddings, then it learns these things and tries to reconstruct the bag of words. There are a couple of different metrics that you can choose. So here we evaluate the match, the Kullback-Leibler divergence, so the difference in fit, and the centroid similarity, sort of like how similar are the topics in an embedding space. We did a human evaluation of the topic quality. So out of 3, so 1 was like not very good, 2 was okay, 3 was excellent. And then, you can obviously also compare the output. There are also metrics like, what is it here? Oh yeah, tau and rho. There are different metrics to evaluate the quality, the coherence of the measures. So how coherent are the topics again, using various metrics. And there's also one that looks at the variety of topics. So does your model, if you ask the model for 10 topics, does it basically find 10 variations of the same topic, or does it find 10 actually different topics? So there are different standard metrics out there in the literature that you can use to evaluate the quality of a model. Many of those are implemented as like automated functions, so you don't have to like code them up yourself.
There is another question. Since modeling topics is not deterministic, would you run topic models several times? How often would you repeat this?
It depends a little bit on your, so the answer is yes, you should run it repeatedly. It depends a little bit on your patience and your confidence in the results. I think like if you run it 3 to 5 times, you'll get like after you've selected all of the parameters, you probably get like a fairly good sense of what are the stable topics, what are the repeat topics, how sensible are those, right? And then you can get a sense of that, but it's definitely a good idea to rerun these a couple of times. So here I actually ran it now with 14. And you can see that that results in like much more varied topics, right? There seems to be fewer repetition. And we can see whether that actually has an effect on also the representation. So if we have 14 topics, it's going to be a bit of a mess to display, but you get different granularity. So also whenever you have topics, you should basically explain why you chose a certain number of topics. There might be a theoretical reasoning for it. You happen to know a priori that there need to be 15 different categories because that's what this topic has, or what this domain, what this problem has, or you've run an analysis like this. So obviously here, having 14 topics, you get much more nuanced or fine-grained characters of what's going on in there.
There is one question. Jay missed it, but which step represents getting word embeddings?
In here, none. This is not on word embeddings. This does not include word embeddings. Yeah. If you're interested in using word embeddings, let me see here. Want to use these? You can go to this GitHub page. Why is it not loading? Interesting. There we go. So you can go to this GitHub page, which is what I showed before, right? So these are the papers associated with it, and then here's like a topic modeling with embeddings. There's an explanation of the architectures, the embedding models you can use. You can use different ones. It has a number of tutorials in Colab that you can run yourself and to understand what's going on and to see the code snippets. It's relatively easy to install and to set up. And there's a whole bunch of background and like questions about it. There's an FAQ essentially on the different ones. There's these essentially supervised, contextualized topic models based on a paper that came out a couple of years ago. And there's a couple, it also includes visualizations and coherence scores, also things like word clouds, which personally I'm not a super great fan of, but my co-authors like them. So, you know, and they can be useful for some things. So this all comes with the package, and you can play around with this.
Thank you. And there is also a doubt of Nikolai. When the cross-country variation is so limited, would it make sense to decrease the alpha?
Yeah. So this is a very good intuition and a good understanding of what's going on, right? If by running these things and observing the output, right, that can inform your choice of hyperparameters like alpha and beta, or the number of topics, right? So this back and forth between looking at graphs and at outputs, but also at the actual topics and maybe at some of the documents to get a better understanding of, am I getting from the models what I would expect to get? And you know, this is obviously a trade-off. If you did this ad infinitum, then you could have just done everything by hand. But if we have even 50,000, you know, wine descriptions, I cannot read all of them manually, right? And so if the topic models can speed up this process for me, and I do like a couple of iterations to choose the parameters, that's already helpful. The other thing I should point out with like stability, so I use this example quite a lot, so I know the data set fairly well, but every time I get slightly different results, but there is some stability. For example, like, you know, German wines always having this like either sweet or acidity and crisp and like green fruit and apple things, and like, you know, sort of Italy having bright drinkable wines that pair well, and you know, things like that. So there are like repeat topics, and it's independent of the number of topics and the exact setting of parameters. So that indicates that there's some stability, but you have to interact with this, right? So this is what I meant, like a topic model is a tool, is an assistance to you, but it doesn't sort of remove all of the work, right? You need to work with it, and you need to sort of get an understanding of what's going on, and then you can get really, really nice insights and results, but it's not sort of like a black box in a fire and forget, which cuts both ways, right? So on the one hand, if you run a topic model the first time and you get crap results, that doesn't mean there isn't anything, right? It just might mean your parameter settings aren't good, right? But on the other hand, you know, if it does mean you will have to, you know, run a couple of times and understand what's going on. And the goal of today was to give you that sense of like, if I suspect something is not right, what are the dials and knobs and levers that I can work with to change how my model reacts and what it gives me, and what should I look out for to make sense of whether this is a reliable result or not.
There are no more questions so far.
Okay. Well, that also, I guess, gets us to the end of the session of today, right? Until 2 o'clock. So if you want to play around with this, you can have the notebook that's out there. You can play around with the contextualized topic models, and there's a whole range of other things. I gave you some of the readings. You can work with the lecture notes, and of course, if you have questions, feel free to send me an email if you want to look more into these things. I see there's one question. Is there a reason to over tweak the model? Yeah, these things are always there, right? So this is the overfitting. So this is typically why you'd want to take a subset of the data to fit the model on, and not the entire data, for speed reasons, but also because then that tells you whether it generalizes or not. So yeah, but you can sort of over tweak things as much as you want. I don't think it's like entirely possible to get a result that's not there, but there's definitely a too much of hand holding for the model. Yeah. All right. Thank you, everybody, for attending. Thanks for the fantastic questions. Really enjoyed it. Very, very thoughtful, insightful questions. Also nicely carried the conversation along. I hope this has opened up some, thoughts, ideas, projects for some of you. I'd also like to thank the whole Hertie team and everybody who has worked tirelessly behind the scenes. It was a fantastic experience as a presenter. Yeah, pleasure to work with you again today. Was a very easy way of going about it. So I wish we could always have online lessons like this. So thanks, everybody. Have fun, and yeah, stay in touch and have fun working with NLP, with computational social science, and doing all the exciting things that we can do these days with all the data and the tools we have available. But be responsible, please. All right. Thanks, everybody. Goodbye.